The universe is trying to kill everything in it. Stars explode, black holes shred matter into nothing, entire galaxies collide, and between all of it, silence so vast and so complete it has its own kind of horror, because the further out you go, the more the beauty peels back. And what's underneath it is something no one warned you about. If you want to keep exploring ideas like this one, make sure to subscribe to the channel. Now let's get started. Beyond Mars lies the asteroid belt, a region stretching roughly between 1.7 and 3.2 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 149 million kilometers. So we're talking about a band of space that starts about 250 million kilometers from Earth at its inner edge and extends out to nearly 500 million kilometers. Now, you've probably seen the asteroid belt depicted in movies as this dense, chaotic wall of tumbling rocks, ships weaving frantically between boulders the size of buildings. That image is almost entirely wrong. The asteroid belt is vast, incomprehensibly vast, and while it contains hundreds of thousands of objects, possibly millions, including the dwarf planet Ceres, the average distance between significant asteroids is around 950,000 kilometers. You could fly a spacecraft straight through and statistically almost certainly never come close to hitting anything. Every space mission we've sent through it has passed safely. But there's something the asteroid belt represents that matters more than its physical danger. It's a graveyard, a museum. The asteroids are leftover material from the formation of the solar system about 4.5 billion years ago. The raw ingredients that never got their chance to become a planet, kept stirred and separated by Jupiter's enormous gravitational influence. When you pass through the asteroid belt, you are moving through ruins, through the pieces of a world that never was. That's its own quiet kind of strange. Now we reach Jupiter, and this is where things start to shift in a way you can feel. Jupiter is a monster. There is no other word for it. It is the largest planet in our solar system, so massive that more than 1,300 Earths could fit inside it. Its great red spot, a storm that has been raging continuously for at least 350 years, possibly longer, is itself larger than our entire planet. The winds inside that storm exceed 600 kilometers per hour. Jupiter sits roughly 778 million kilometers from the Sun on average. The Juno spacecraft, launched in 2011 and still operating as of the time this script was written, has been orbiting Jupiter since 2016 and has sent back images and data that have rewritten our understanding of this world. We discovered that Jupiter's poles are covered in geometric cyclone clusters, oval storms packed so tightly together they look almost mathematically intentional. At the North Pole, there's a central storm surrounded by 8 others. At the south, 5 surround the central one. Nobody fully understands why they're arranged this way. The patterns suggest organizational dynamics in atmospheres that our current models weren't predicting. Jupiter also has a moon called Europa, and Europa might be one of the most important places in the entire solar system. Beneath its icy shell, which is estimated to be between 15 and 25 kilometers thick, sits a global liquid water ocean that has more water in it than all of Earth's oceans combined. Tidal heating from Jupiter's gravitational pull keeps that water liquid, and where there's liquid water, there could be chemistry, there could be energy gradients, there could be, in theory, life. NASA's Europa Clipper mission launched in October 2024. It is currently en route and expected to begin its orbital survey in 2030. We are going there. We are actually going there to find out. But here's the terrifying part about Jupiter. Not the storms, not even the possibility of alien life nearby. It's the radiation. Jupiter's magnetic field is the most powerful of any planet in the solar system, about 20,000 times stronger than Earth's. and it traps charged particles in radiation belts around the planet that are so intense they would deliver a lethal dose to an unprotected human in a matter of minutes. Even Juno, a radiation-hardened spacecraft, has a limited mission life because of the cumulative damage. Jupiter is beautiful and it is extraordinary, and it is also, quite simply, lethal to approach. We are still inside our solar system. We haven't even reached the halfway point of our outward journey, so you've made it past Jupiter. You're still alive, barely, hypothetically, and you're pressing onward. The sun behind you is already noticeably smaller than it looks from Earth. Not dramatically so, not yet, but enough that you'd notice. Enough that the warmth you've felt your entire life, that baseline radiation that your skin has always known, is starting to feel a little more distant, a little more like a memory. Let's talk about Saturn. If Jupiter is a monster, Saturn is a poet. There's something about it that defies expectation every single time you see a real image of it. Not an artist's rendering, not a diagram, an actual photograph. Because when you see Saturn through a telescope for the first time, and I mean really see it, rings and all, unmistakable and impossible looking, your brain almost refuses to accept it as real. It looks like something someone put there on purpose, like a prop, like the universe got a little theatrical and decided one planet deserved to be genuinely, ostentatiously, almost arrogantly beautiful. Saturn sits about 1.4 billion kilometers from the Sun. A signal from Earth takes roughly an hour and 20 minutes to reach it at the speed of light. The Cassini spacecraft, one of the most successful deep space missions in human history, orbited Saturn from 2004 to 2017, 13 years of up-close science that utterly transformed our understanding of this system. When Cassini finally ran out of fuel, scientists deliberately plunged it into Saturn's atmosphere to avoid any chance of contaminating the moons below with Earth microbes. It burned up, transmitting data until the very last second. That mission gave us hundreds of thousands of images. It discovered active geysers on the moon Enceladus. It mapped Titan's methane lakes. It changed everything. And those rings, those breathtaking, iconic rings, are not permanent. They are, in cosmic terms, young. Estimates from Cassini's data suggest the rings formed somewhere between 10 million and 100 million years ago. The solar system is 4.5 billion years old. The rings have existed for at most about 2% of that time, and they're disappearing. Ring rain, charged particles being pulled down into Saturn's atmosphere by its magnetic field, is gradually draining the rings away. In another 100 million years or so, they'll be mostly gone. Again, we are living in a rare window. We exist at the one moment in the entire multi-billion-year story of this solar system when Saturn looks the way it does in every poster, every textbook, every dream a child has ever had about outer space. That window too is closing now. Enceladus. We need to talk about Enceladus because this small, icy moon of Saturn, only about 500 kilometers across, turned out to be one of the most astonishing discoveries of modern planetary science. Cassini flew through plumes of material erupting from the south pole of Enceladus and sampled what was in them: water vapor, ice particles, organic molecules, the carbon-based building blocks of chemistry as we know it, molecular hydrogen, which can be produced by hydrothermal reactions between water and rock, silica particles that suggested water temperatures above 90 degrees Celsius at the seafloor. Everything that scientists consider a prerequisite for life as we understand it was present in those plumes, shooting out into space for free, like Enceladus was offering them to whoever happened to be passing by. It is not an exaggeration to say that Enceladus might harbor life right now, today, in the ocean beneath its shell. We don't know. We haven't proven it. Science requires evidence, not hope, and the evidence so far is suggestive rather than conclusive. But the conditions are there. And that means that when you look at Saturn in your night sky, glowing steadily among the stars, one of its small moons might be home to living things that have never once seen sunlight, never once felt warmth from any star, living their entire existence in a dark, pressurized ocean kilometers beneath a frozen shell, heated by the geological violence of tidal forces, life completely alien, possibly already existing, somewhere between 1 and 1.7 billion kilometers from where you are sitting. Think about that for a second. Continuing outward, we reach Uranus and Neptune, the ice giants, the forgotten outer planets, the ones that somehow always get treated like footnotes, even though they are each enormous and deeply, genuinely weird. Uranus sits about 2.9 billion kilometers from the Sun. It takes sunlight roughly 2 hours and 40 minutes to reach it, and Uranus has a problem, or rather, a feature so strange that it deserves its own paragraph. It rotates on its side, not slightly tilted like Earth, which leans at about 23 degrees. Uranus is tilted at 98 degrees. It essentially rolls around the Sun like a bowling ball, rather than spinning upright like a top. Its north pole spends about 42 Earth years pointed almost directly at the Sun, then 42 years pointed away into deep darkness. The seasons on Uranus are unlike anything in the rest of the solar system. The leading theory is that something massive, another planet-sized body, slammed into Uranus billions of years ago and knocked it over. A collision so violent it permanently changed the orientation of an entire world, and the evidence of that violence is still written in the tilt of the planet today. We have visited Uranus exactly once. The Voyager 2 spacecraft flew past in January 1986. Once in the entire history of spaceflight. Since then, everything we've added to our understanding of Uranus has come from ground-based telescopes and the Hubble Space Telescope, and more recently the James Webb Space Telescope, which has given us new details about its atmosphere and ring system. There are discussions about sending a dedicated mission. A proposed Uranus orbiter and probe was ranked the top priority for the next decade of planetary science by the 2023 Planetary Science Decadal Survey. But as of now, no mission has been formally approved and launched. Uranus remains one of the least explored major planets in our solar system, and every model we build of it has enormous gaps. We don't fully understand a planet in our own solar system. That's humbling in a very particular way. Neptune is further still, about 4.5 billion kilometers from the Sun, which means it takes light roughly 4 hours and 10 minutes to get there. Neptune was predicted mathematically before it was observed. In the 1800s, astronomers noticed that Uranus wasn't moving quite where their calculations said it should be. Something was pulling it. Something was out there, gravitationally nudging the orbit of an entire planet from an unknown location. Mathematicians Urbain Le Verrier and John Couch Adams independently worked out roughly where the mystery object must be. And when observers pointed their telescopes to those predicted coordinates in 1846, Neptune was there, within 1 degree of where the math said it would be. That's what physics is. That's what mathematics is. The universe running on rules consistent enough that you can predict the existence of an unseen world from the misbehavior of another one, with nothing but a pencil and paper. Neptune's largest moon, Triton, orbits in the wrong direction. Every other large moon in the solar system orbits in the same direction its planet rotates. Triton orbits backward. The overwhelming consensus is that Triton was captured from the Kuiper belt, grabbed by Neptune's gravity and pulled into orbit. And because it's orbiting the wrong way, tidal forces are slowly dragging it inward. In roughly 3.6 billion years, Triton will cross what's called the Roche limit, the distance at which gravitational tidal forces will overcome the Moon's own structural integrity, and it will be torn apart. The debris will form a ring system around Neptune that could rival Saturn's 3.6 billion years from now. Neptune gets rings. The universe is always building something, or destroying something, often both at the same time. Now we step past Neptune. And here's where the architecture of our solar system becomes genuinely surprising in a way most people never learn about. Past Neptune is the Kuiper Belt, a region extending from about 30 to 50 astronomical units from the Sun, packed with icy objects left over from the formation of the solar system. Pluto is there, Eris, Makemake, Haumea. These dwarf planets are remnants, fossils, chunks of the primordial material that seeded the outer solar system. The New Horizons spacecraft flew past Pluto in July 2015 and sent back images that shocked the entire scientific community. We expected a dead, cratered, geologically inert rock. What we got was a world with mountains made of water ice rising 3,500 meters high, a vast heart-shaped nitrogen glacier, the size of Texas and Oklahoma combined, called Tombor Regio, evidence of atmospheric haze layers and indications of possible past subsurface activity. Pluto wasn't dead. Pluto was alive in ways nobody had fully predicted, and New Horizons had only a few hours of close encounter to capture all of it, because at that speed and at that distance, you don't stop, you don't slow down. You fly through and keep going. That data took 16 months to fully download back to Earth, transmitted at a rate slower than an old dial-up internet connection, across a distance so vast that even light took 4.5 hours to bridge it. And then past the Kuiper Belt, something else lurks, something that reframes the entire scale of our solar system. The Oort cloud. The Oort cloud is a theoretical shell of icy bodies, comets, frozen debris that is believed to extend from somewhere around 2,000 astronomical units all the way out to perhaps 100,000 astronomical units from the Sun. That outer edge sits about 1.6 light-years away. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years distant, which means the gravitational influence of our Sun, the outer edge of what you could legitimately call our solar system, reaches almost halfway to the nearest star. The solar system is not the 8 planets and a few moons you learned about in school. It is a sphere of influence nearly 2 light-years across, and the vast, overwhelming majority of it is a dark, frozen wilderness that no spacecraft has ever visited, that we cannot directly observe, that we know exists, mostly because of the long-period comets it occasionally sends falling inward toward the Sun. We have a neighborhood, we just haven't seen most of it, and the Sun's gravitational pull, as vast as it is, as far as it reaches, eventually loses its grip. There's a boundary, not a physical wall, but a real, measurable transition zone called the heliopause. This is where the solar wind, that constant stream of charged particles flowing outward from the Sun in all directions, finally becomes too weak to push back against the interstellar medium, the sparse gas and charged particles that fill the space between stars. The Voyager 1 spacecraft, launched in September 1977, crossed the heliopause in 2012. It is the only human-made object that has definitively done so. As of the time this script was written, Voyager 1 is approximately 23 billion kilometers from the Sun, about 154 astronomical units out. It is traveling at roughly 61,000 kilometers per hour, and it will take another 300 years just to reach the inner edge of the Oort cloud, and about 30,000 years to pass through it entirely. 30,000 years. At 61,000 kilometers per hour, that is the size of our solar system. And beyond the heliopause, beyond the Oort cloud, in the true interstellar space between stars, that's where the next layer of terror begins. And we haven't even gotten there yet. You are now beyond the solar system. Let that settle for a moment. Behind you, impossibly far behind you, is a small, average, middle-aged star, one of roughly 200 billion to 400 billion stars in the Milky Way galaxy alone. Around that star orbits a pale blue dot, third from the center, covered in oceans, wrapped in a thin skin of atmosphere, crawling with 8 billion people who are mostly unaware of how extraordinarily fragile their situation is. That dot is your home. Everything you have ever known, everyone you have ever loved, every city, every mountain, every ocean, every moment of recorded human history, all of it fits on that dot. And from where you are now, you cannot see it anymore with the naked eye. The sun, your sun, our sun, the thing that has driven every sunrise you've ever witnessed, that powers every plant and every storm and every ocean current on Earth. From interstellar space, it is just another star, a slightly brighter one maybe, if you know exactly where to look. But just a star, one among hundreds of billions. That's not a metaphor, that's physics. So what does interstellar space actually look like? What is it? Most people imagine it as pure emptiness, a perfect vacuum, nothing at all. And while it is extraordinarily sparse compared to anything we experience on Earth, it is not actually empty. The interstellar medium, the material that fills the space between stars, is a mixture of gas and dust, mostly hydrogen and helium, with trace amounts of heavier elements, complex molecules and charged particles. The density is almost incomprehensible in its thinness. On average, there is about 1 atom per cubic centimeter of interstellar space. 1 atom. In a cube 1 centimeter on each side. By comparison, the air you're breathing right now contains roughly 2.7 times 10 to the 19th power molecules per cubic centimeter. That's 27 million trillion molecules per cubic centimeter. And interstellar space has 1 atom, but here's the thing about that near-nothingness. It is not uniform, it has structure, it has regions of higher and lower density, clouds of cold gas, bubbles carved out by supernova explosions, filaments of warmer ionized hydrogen. Our solar system is currently moving through a region called the local interstellar cloud, a warm, partially ionized bubble of gas about 30 light-years across. We've been inside it for somewhere between 45,000 and 150,000 years. Before that, we were in an even larger, hotter region called the local bubble, a cavity in the interstellar medium about 1,000 light-years across that was likely carved out by a series of supernova explosions somewhere between 10 and 20 million years ago. We live inside a scar left by dead stars, and those dead stars, those supernovae that carved the bubble we're drifting through, they matter. Because the heavy elements that make up your body, the calcium in your bones, the iron in your blood, the oxygen in your lungs, none of those were made in the Big Bang. The Big Bang produced hydrogen, helium, and tiny traces of lithium. Everything heavier than that was forged in the cores of stars and then scattered across space when those stars died violently. You are, in the most literal and scientifically accurate sense possible, made of material that was once inside a star, multiple stars, stars that lived and burned and exploded long before our sun was even born. You are not just looking at the universe. You are the universe looking at itself now, the nearest star, Proxima Centauri. 4.2 light-years away, a light-year is the distance light travels in 1 year, moving at just under 300,000 kilometers per second. In 1 year, light covers roughly 9.5 trillion kilometers. Multiply that by 4.2, and Proxima Centauri is about 39.9 trillion kilometers away. 39.9 trillion kilometers. The fastest spacecraft humanity has ever launched is the Parker Solar Probe, which reached speeds of around 692,000 kilometers per hour during its close passes of the Sun. At that speed, to reach Proxima Centauri, you would need approximately 6,500 years, 6.5 millennia, longer than all of recorded human history. The ancient Egyptians built the pyramids roughly 4,600 years ago. We are not even that old as a civilization, and yet the nearest star would take longer than our entire recorded existence to reach at the fastest speed we've ever achieved. And Proxima Centauri isn't even particularly interesting as a destination. It's a red dwarf, a small, dim, temperamental star that regularly blasts its surroundings with powerful flares. It has at least 2 known planets. One of them, Proxima Centauri b, orbits in what's called the habitable zone, the range of distances from a star where liquid water could theoretically exist on a planetary surface. This discovery, announced in 2016, generated enormous excitement. A potentially habitable planet around the nearest star. It seemed almost too good to be true. It probably is too good to be true, because Proxima Centauri is a flare star and the radiation environment around it is savage. Proxima b, despite being in the habitable zone in terms of temperature, is likely bombarded by ultraviolet and X-ray radiation at levels that would make the surface extraordinarily hostile to life as we know it, without a strong magnetic field and a thick protective atmosphere, both of which we don't yet know whether Proxima b has. That surface might be effectively sterilized by stellar activity on a regular basis. Our nearest neighbor might be a dead end, literally. But the distance isn't the only thing that makes interstellar travel terrifying. It's what the journey itself would do to you, in the void between stars, away from any planetary magnetic field, away from the sun's protective bubble. You are exposed to galactic cosmic rays, high-energy particles, mostly protons, accelerated to near-light speed by supernova shock waves and other violent astrophysical processes. These particles don't just pass through you, they smash through your DNA, they ionize the atoms in your cells. The damage they cause is cumulative and serious: increased cancer risk, potential damage to the central nervous system, possible cognitive effects. Studies on astronauts who have spent extended time on the International Space Station, which is still inside Earth's magnetosphere and thus significantly protected, already show measurable changes in brain structure, fluid distribution around the brain and spine, and visual disturbances caused by intracranial pressure changes, and the station is only about 400 kilometers up, still wrapped in Earth's protective magnetic embrace on a multi-year interstellar voyage, with no protection. The cosmic ray exposure alone could cause serious neurological damage before you ever arrived anywhere. And then there's the question of speed. To reach even the nearest star in any reasonable human timeframe, you'd need to travel at a significant fraction of the speed of light. Let's say you somehow achieved 10% of light speed, which would require energy outputs so enormous they're essentially fantasy with current technology. But let's imagine it. At 10% light speed, you'd reach Proxima Centauri in about 42 years, a human lifetime, barely. But at those speeds, even a single grain of sand, a particle of interstellar dust a fraction of a millimeter across, would hit your spacecraft with the energy of a small explosive. The interstellar medium, that 1 atom per cubic centimeter near vacuum we talked about, suddenly becomes a sand-blasting environment. Your hull would need shielding that we don't know how to build. The engineering challenges are not just difficult. They may be, with anything resembling our current understanding of materials science, effectively insurmountable. The universe does not make it easy to leave home. Now let's talk about something that doesn't get enough attention, something that sits quietly in the background of every conversation about interstellar travel and deep space exploration, never quite named but always there, always pressing: loneliness, not the emotional kind, though that too obviously would be overwhelming. I mean the physical, informational kind, the communication lag. On Mars, there's a delay of up to 22 minutes each way. Frustrating but workable. At the distance of Proxima Centauri, a message sent at the speed of light takes 4.2 years to arrive and another 4.2 years for the response to return. 8.4 years for a single exchange of information. You could send a message and be dead of old age before the reply arrives. There is no community at that distance, no shared news, no updates from home, no connection to the civilization that built you and launched you and hoped for you. You would be, in any meaningful sense, completely and permanently alone, drifting through a dark between two islands of light, with nothing but the contents of your own spacecraft and the people, if any, aboard it. Psychologists who study isolation, researchers who work with Antarctic winter overcrews, with submarine crews, with cosmonauts on long-duration missions, talk about something called the third quarter phenomenon, a predictable psychological low point that hits when people realize they are closer to the end than the beginning of a long, isolated period. The end, in this case, would be decades away. The beginning would be decades behind you. There might not be a psychological concept that adequately describes what that does to a mind. We are biological creatures. We evolved in small groups on a green and blue world, surrounded by other living things. We are not built for the between. We are not built for the dark. And yet we keep going, because here is the other side of all this terror. The side that I never want you to lose sight of as we travel further and further from everything familiar. The fact that we know any of this, the distances, the radiation, the flares, the cosmic ray flux, the psychological effects of isolation. The fact that we have measured these things and modeled them and thought carefully about them is itself one of the most astonishing things our species has ever done. Voyager 1, that little spacecraft launched in 1977, was built with computing power roughly equivalent to a modern pocket calculator. The people who designed it used slide rules for some of their calculations, slide rules, and they sent it on a trajectory so precisely calculated that it used gravitational assists from Jupiter and Saturn to slingshot itself outward, and it is still transmitting data from interstellar space nearly 50 years later. The James Webb Space Telescope, which began science operations in 2022, can detect the light from galaxies so distant that the light we're receiving left them when the universe was less than 500 million years old. It has already given us images of galaxies that existed when the universe was a toddler, structures that no human eye had ever seen before in any form, and it has begun analyzing the atmospheres of planets orbiting other stars, searching for chemical signatures that might suggest biology. We are looking for life, methodically, seriously, with the best instruments our civilization has ever built. That's not terrifying, that's magnificent, but the magnificence and the terror are not opposites. They are the same thing, seen from different angles. The universe is vast enough to make you feel utterly, cosmically insignificant. And it is also complex enough, structured enough, rule-governed enough, that a species that evolved on a small rock around an ordinary star has been able to understand it, measure it, and reach out into it, just a little, with instruments made of metals and glass and mathematics. That is the human story. That is our story, and we are nowhere near the end of it, but we're also nowhere near the end of our journey today, because we've only made it to interstellar space, the region between stars within a single galaxy. We haven't talked about what happens when you zoom out further, when you start thinking in terms of the galaxy itself, the supercluster, the observable universe, the things at the absolute edge of what can even theoretically be detected. That's where the real strangeness lives. That's where the physics starts to break in ways that even the best minds on the planet don't fully understand. That's where the universe stops being a place you can navigate and becomes something else entirely. And that's exactly where we're going next. Let's zoom out, not a little. Not the kind of zoom where you go from your city to your country on a map. I mean the kind of zoom that makes your brain quietly short-circuit if you let it fully land. The kind where every time you think you've grasped the scale, the universe casually reveals another layer of itself that dwarfs everything you just processed. We've left the solar system. We've acknowledged the terrifying distances between stars. Now let's talk about the structure those stars belong to, the architecture that contains them, the galaxy, our galaxy, the Milky Way. You've seen it, maybe. On a clear night, far from city lights, a hazy band of light stretching across the sky from horizon to horizon, soft, diffuse, almost gentle-looking. That band is the combined glow of hundreds of billions of stars, so distant and so densely packed along our galaxy's disk that individual stars blur together into a wash of light. You are inside it, looking outward from a position roughly 26,000 light-years from the center, sitting on one of the spiral arms, the Orion Arm, sometimes called the Orion Spur, a relatively minor feature between two larger arms called Perseus and Sagittarius. The Milky Way is approximately 100,000 light-years across. Some more recent estimates, drawing on data from the Gaia Space Telescope, a European Space Agency mission that has been mapping the positions and motions of nearly 2 billion stars with extraordinary precision, suggest the disk might extend up to 170,000 light-years in diameter when you account for its warped, flared outer edges. Yes, the Milky Way is not flat, it's warped, like a vinyl record left in the sun, curving upward on one side and downward on the other, likely due to past gravitational interactions with neighboring dwarf galaxies. Our galaxy is lopsided, and we're in it. The disk is relatively thin, only about 1,000 light-years thick in most places, but it's embedded in a much larger, spherical halo of older stars, globular clusters, and dark matter that extends for hundreds of thousands of light-years in every direction. The Milky Way is not just the flat spiral you've seen in illustrations. It's a three-dimensional structure of enormous complexity, with a history written in the orbits and compositions of its stars going back almost to the beginning of the universe itself. And our solar system is orbiting the center of all of it. Right now, as you sit here watching this, our entire solar system, the sun, the planets, everything, is moving through the galaxy at roughly 828,000 kilometers per hour. We complete one full orbit of the galactic center approximately every 225 to 250 million years. That unit of time even has a name. It's called a cosmic year or a galactic year. The last time our solar system was in the same position in the galaxy that it occupies today, the Triassic period was just beginning on Earth. The first dinosaurs were about to evolve. We have gone around exactly once since the age of dinosaurs began. We are passengers on a journey so vast we can barely perceive its happening. Now, the center. If the outer reaches of the Milky Way are wild and strange, the center is something else entirely. Something that earned its strangeness through violence on a scale that makes everything we've discussed so far feel almost quaint. At the very heart of our galaxy, roughly 26,000 light-years from where we are, sits an object called Sagittarius A star. It is a supermassive black hole, and when I say supermassive, I don't mean large in the way that Jupiter is large compared to Earth. I mean large in a way that requires you to abandon normal intuitions about size entirely. Sagittarius A star has a mass of approximately 4 million times the mass of our Sun, 4 million solar masses compressed into a region of space roughly the size of our solar system out to the orbit of Mercury. The event horizon, the point of no return, the boundary beyond which not even light can escape, has a radius of about 12 million kilometers. For comparison, our Sun's radius is about 696,000 kilometers. The event horizon of Sagittarius A star is roughly 17 times wider than the entire Sun. In April 2019, the Event Horizon Telescope collaboration released the first ever image of a black hole's shadow, The supermassive black hole at the center of a galaxy called Messier 87, about 53 million light-years away. Then in May 2022, they did it again, and this time the image was of Sagittarius A star itself, our own galactic black hole. For the first time in human history, we had a direct image of the gravitational monster sitting at the center of our galaxy. It was blurry, orange-ringed, and almost modest-looking, and it was one of the most profound scientific achievements in the history of astronomy. But here's what that image doesn't convey, what the clean, carefully processed photograph doesn't show you. The environment around Sagittarius A star is not calm. It is a war zone. The galactic center is packed with young, massive stars that have no business being there, stars so large and so luminous that they should have been torn apart by tidal forces long before they could form, and yet somehow they exist, orbiting within a fraction of a light-year of the black hole itself. There are clouds of hot gas spiraling inward. There are X-ray flares that erupt from the accretion region around the black hole multiple times every day, briefly outshining the entire galactic core in high-energy radiation. There are enormous gamma-ray bubbles, called Fermi bubbles, discovered in 2010 using the Fermi Gamma-Ray Space Telescope, extending roughly 25,000 light-years above and below the galactic plane, relics of some enormous energy release from the galactic center in the past. We're not entirely sure what caused them, possibly a period of intense star formation, possibly past activity from Sagittarius A star itself when it was feeding more actively and releasing jets of energy that blasted outward through the galaxy. The center of the Milky Way is a place of extraordinary, almost incomprehensible violence, and we orbit it. Every 230 million years we make another loop around that monster. But black holes aren't only at galactic centers. They're scattered throughout the galaxy, and they come in sizes that should genuinely unsettle you. Stellar mass black holes, the kind formed when a massive star collapses at the end of its life, typically range from about 5 to several tens of solar masses. They're created in events called core collapse supernovae, explosions so powerful they briefly outshine entire galaxies. In the final moments of a massive star's life, the core collapses in less than a second. The outer layers rebound and are blasted outward in a shockwave, and what remains is either a neutron star or, if the collapsing mass is sufficient, a black hole. Let's talk about neutron stars for a moment, because they deserve their own pause. A neutron star is what you get when a star between roughly 8 and 20 solar masses reaches the end of its fuel supply and collapses, but doesn't quite have enough mass to form a black hole. Instead, the core is compressed to a sphere roughly 20 kilometers in diameter. 20 kilometers! You could drive across a neutron star in about 12 minutes. And yet that sphere contains between 1 and 2 times the mass of our entire Sun. The density is beyond anything your intuition is equipped to handle. A single teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. The gravity at the surface is about 200 billion times stronger than Earth's gravity. If you fell onto a neutron star from a height of 1 meter, you would hit the surface at about 2 million kilometers per hour. The surface itself is thought to be a crystalline lattice of atomic nuclei, a crust harder than any material that exists or could exist anywhere else in the known universe. Beneath that crust, the matter transitions into something so exotic and so extreme that physicists genuinely disagree about what state it's in. Some models suggest the core might contain strange quarks. Others propose exotic states of matter that have no analog anywhere in normal experience. We simply don't know, because the physics in those conditions pushes right up against, and possibly beyond, the limits of our current understanding. Some neutron stars rotate, and some of them rotate fast, incredibly fast. Objects called millisecond pulsars spin hundreds of times per second, beaming radiation from their magnetic poles like cosmic lighthouses sweeping the galaxy. The fastest known pulsar, PSRJ-17, rotates 716 times per second, an object the size of a city, containing more mass than the Sun, spinning more than 700 times every second. The surface at the equator is moving at roughly 24% of the speed of light. This is a real thing. This exists in our galaxy right now. And then there's the question of what black holes do when they find each other. In September 2015, the LIGO Observatory, the Laser Interferometer Gravitational Wave Observatory, detected something that had been predicted by Einstein's general theory of relativity 100 years earlier, but never directly observed. Gravitational waves, ripples in the fabric of space-time itself, caused by two black holes, one about 29 solar masses, the other about 36, spiraling inward toward each other over billions of years, and finally merging in a collision that lasted less than a second. In that fraction of a second, more energy was released than all the stars in the observable universe emit in that same moment of time. Combined, every star, every sun, every furnace of nuclear fire burning across the cosmos. And this single collision, in that instant, outshone them all. The collision happened about 1.3 billion light-years away. The gravitational waves from it traveled outward at the speed of light, stretching and squeezing space-time as they passed through it. And 1.3 billion years later, when the light from that event was still 500 million years away from reaching us, the wave arrived at Earth, and it squeezed our planet, not enough to feel. The distortion was about 1,000th the width of a proton, but LIGO measured it, 2 tunnels 4 kilometers long, with laser beams bouncing back and forth inside them, detected a change in length smaller than the nucleus of an atom. That is the sensitivity of human instrumentation. That is what we built. That is what we are capable of. Since that first detection, LIGO and its partner observatories, Virgo in Italy and Kagra in Japan, have detected dozens of gravitational wave events, merging black holes, merging neutron stars, possibly even a black hole merging with a neutron star, each one a catastrophic collision billions of light-years away, its echo arriving here as a whisper, so faint it takes the most sensitive scientific instrument ever built to notice. The universe is constantly colliding with itself. And we are finally learning how to listen. Now let's pull back even further, because we've been talking about our galaxy as though it exists in isolation, as though the Milky Way is the whole story. It isn't. Not even close. The Milky Way is part of a small collection of galaxies called the Local Group, about 50 to 80 galaxies, depending on how you count the very small ones. The largest members are the Milky Way and the Andromeda Galaxy, Messier 31, which sits about 2.5 million light-years away and is, with the naked eye, the most distant object a human can see without a telescope. It appears as a faint fuzzy smudge in the constellation Andromeda on a clear night. Unremarkable, easy to miss. But Andromeda is not small. It is larger than the Milky Way. It contains roughly 1 trillion stars compared to our estimated 200 to 400 billion, and it is heading directly toward us. Andromeda and the Milky Way are on a collision course. The two galaxies are approaching each other at roughly 110 kilometers per second. In approximately 4.5 billion years, they will collide and begin the process of merging into a single, larger elliptical galaxy, a structure astronomers have already given a provisional name, Milkomeda, or sometimes Milkdromeda. Yes, astronomers have a sense of humor. Now, when you hear the word collision between two galaxies, you might imagine an explosion. Two enormous structures smashing into each other catastrophically, stars raining down, everything destroyed. But that's not really how it works, because galaxies are mostly empty space. The stars within them are so far apart that when two galaxies interpenetrate, Most stars don't actually collide with each other. They pass through, swinging around each other, gravitationally, dramatically disrupted, but not necessarily destroyed. The galaxy shapes distort. Long tidal tails of stars are flung outward. Clouds of gas are compressed, triggering enormous bursts of new star formation. The whole process plays out over hundreds of millions of years. Our solar system will probably survive. It might even be flung into a completely different region of the merged galaxy. Our night sky, 4.5 billion years from now, will look utterly unrecognizable. More stars, different patterns, different neighbors. The familiar constellations, which are already slowly shifting and will be unrecognizable in 100,000 years as the stars move through the galaxy, will be replaced entirely by a sky we cannot even begin to predict. Everything familiar on a long enough timeline becomes unrecognizable, and beyond the local group, beyond the small cluster of galaxies we call home, the Virgo supercluster, a vast assemblage of galaxy groups and clusters roughly 110 million light-years across, containing the local group as just one of its many constituents. And even that is not the top of the hierarchy. The Virgo supercluster is itself just one lobe of an even larger structure called the Laniakea supercluster, a name derived from Hawaiian, meaning immeasurable heaven. A supercluster 500 million light-years across, containing the mass of roughly 100 million billion suns and home to approximately 100,000 galaxies. Laniakea was only identified and mapped in 2014 using Hubble Space Telescope data and a meticulous analysis of galaxy motions. It turns out that galaxies don't just drift randomly, they flow. They move toward gravitational attractors, regions of higher density that pull surrounding matter inward over billions of years. By mapping those flows, scientists were able to trace the boundaries of our supercluster and discover that the Milky Way sits near the outer edge of Laniakea, slowly drifting toward its gravitational center, a region called the Great Attractor, about 250 million light-years away. We are being pulled, right now, by something enormous, towards something enormous, and for most of human history, we didn't even know it was happening. If you are enjoying this journey, make sure to subscribe. You will be part of a community that explores the cosmos together. Let's keep pulling back, because we've been doing something this entire time that I want you to notice. Every time we've zoomed out, from the Moon to Mars, from Mars to the outer solar system, from the solar system to interstellar space, from interstellar space to the galaxy, from the galaxy to the supercluster, every single time the universe has revealed another layer of itself that was invisible from the previous scale, another structure, another pattern, another level of organization that you simply could not see until you stepped back far enough. And every single time, the scale has been larger than the thing before it by a factor that strains language to describe. We're about to do it again, and this time, the step outward is the biggest one yet. Dosm out far enough that entire superclusters shrink to barely visible smudges, and something extraordinary appears. The universe is not a random scattering of galaxies. It is not a uniform fog of matter distributed evenly in all directions. It has structure, enormous, breathtaking, almost architectural structure, organized on scales so vast that the superclusters we just talked about are merely the building blocks of something bigger still. What you see, when you map the positions of millions of galaxies across hundreds of millions of light-years, is a web, the cosmic web. Long filaments of galaxies and dark matter stretching across hundreds of millions of light-years, connecting at dense nodes where massive galaxy clusters sit like junctions in a network. Between the filaments, enormous empty spaces, cosmic voids, where almost nothing exists. The whole structure looks, with a familiarity that is either poetic or deeply unsettling depending on your mood, like a neural network. Like the inside of a brain, like the web of connections between neurons, scaled up to the size of the observable universe. Nobody designed this, nobody planned it. It emerged from the initial conditions of the Big Bang, tiny quantum fluctuations in the density of the very early universe, inflated to cosmic scales during a period of extraordinarily rapid expansion called inflation, then amplified over 13.8 billion years by gravity pulling matter together along those original density variations. The web is the fossil record of the universe's earliest moments. It is the grown-up version of seeds planted in the first fraction of a second of existence, and we mapped it, using surveys like the Sloan Digital Sky Survey, which catalogued the positions of hundreds of millions of galaxies, and more recently the Dark Energy Spectroscopic Instrument, DESI, which has been building the largest three-dimensional map of the universe ever constructed, measuring the positions and distances of tens of millions of galaxies to understand how the universe's expansion has changed over time. DESI released early results in 2024 that sent ripples through the cosmology community, suggesting the nature of dark energy, the mysterious force driving the universe's accelerating expansion, might be more complex than the simple cosmological constant Einstein originally proposed. The story of what the universe is made of and how it is evolving is still being written in real time by scientists working right now. But let's stop on those voids for a moment, because they don't get enough attention and they deserve it. The cosmic voids are the spaces between the filaments, regions of space that are genuinely, almost completely empty. The largest known void, called the Boötes void, sometimes called the Great Nothing, is roughly 330 million light-years across. Inside a region that enormous, there are almost no galaxies. A handful, maybe 60, have been found within it, compared to the thousands you would expect if matter were distributed evenly. It is a bubble of near-nothingness so large that if our Milky Way were inside it, we would have looked out at the universe for most of human history and seen almost nothing. The nearest galaxies would have been so distant that for most of our existence, before the era of large telescopes, we might have concluded we were alone in an empty universe. The Boötes void was discovered in 1981 when astronomer Robert Kirshner and his colleagues were mapping galaxy distributions and found this inexplicable absence. Kirshner reportedly said at the time that it was so large it shouldn't exist, that their understanding of how structures form in the universe didn't predict anything like it. Our models have since improved, and we now understand that voids are a natural feature of cosmic web formation. But the Boötes void is still on the larger end of what models easily explain, and its origin and exact nature remain an active area of research. P-space on a cosmic scale is not the absence of something interesting. It is one of the most interesting things there is. Now, dark matter. We have to talk about dark matter because it is simultaneously one of the most important things in the universe and one of the things we understand least about it. And the gap between how important it is and how little we understand it is, frankly, one of the most humbling facts in all of science. Here's the situation. When astronomers measure how fast galaxies rotate, specifically how fast stars at the outer edges of spiral galaxies are orbiting the galactic center, they find something that doesn't add up. Based on the amount of visible matter in a galaxy, the stars at the outer edges should be orbiting much more slowly than the ones near the center, the same way the outer planets in our solar system move more slowly than the inner ones. But they don't. Stars at the outer edges of galaxies move at roughly the same speed as stars much closer to the center. The rotation curve is flat when it should be declining. The only way to explain this is if there is significantly more mass in and around the galaxy than we can see. Mass that doesn't emit light, doesn't reflect light, doesn't interact with electromagnetic radiation in any detectable way. It only makes itself known through its gravitational influence. We call it dark matter, and there's a lot of it. Current estimates suggest that dark matter makes up roughly 27% of the total energy content of the universe. All the ordinary matter, every star, every planet, every gas cloud, every human being, every atom you have ever seen or touched or been made of, accounts for only about 5%. 5% of the universe is the stuff we can actually see and measure directly. The rest is dark matter, dark energy, and our own uncertainty. Dark matter has never been directly detected. Every attempt to catch dark matter particles in underground laboratories, shielded from cosmic rays, using ultra-sensitive detectors cooled to near absolute zero, has so far come up empty, or rather, has produced results consistent with no detection. We know it's there because of what it does gravitationally. We see its effects in the rotation of galaxies, in the way galaxy clusters bend and distort light from objects behind them through gravitational lensing, in the large-scale structure of the cosmic web itself, which wouldn't have the filaments and nodes it has without dark matter providing the gravitational scaffolding. But what it actually is, what particle or particles constitute it, whether it's one thing or many, whether it has any interactions beyond gravity, we genuinely do not know. This is not a minor gap. This is not a footnote. 27% of the universe is made of something we cannot identify, and we've been trying seriously for decades. And then there's dark energy. If dark matter is humbling, dark energy is something closer to philosophically destabilizing. In 1998, two independent teams of astronomers were studying a particular type of exploding star, a type Ia supernova, using them as what cosmologists call standard candles. Because type Ia supernovae always explode with roughly the same intrinsic brightness, you can compare how bright they appear to how bright they should be and calculate their distance very precisely. Both teams were using these measurements to map the expansion of the universe, expecting to find that the expansion was slowing down over time. Gravity pulls things together. The universe is full of matter. Matter creates gravity. Gravity should be gradually decelerating the expansion set in motion by the Big Bang. What they found instead stunned the entire scientific world. The expansion of the universe is not slowing down. It is speeding up. The universe is expanding faster and faster as time goes on. Something is pushing everything apart with increasing urgency. Something with negative pressure. Something that acts in the opposite direction to gravity on cosmic scales. Something that permeates all of space uniformly and whose energy density does not dilute as the universe expands. We called it dark energy, and it makes up roughly 68% of the total energy content of the universe. 68%. The single largest component of everything that exists, and we have essentially no idea what it is. The simplest mathematical description is Einstein's cosmological constant, a term he actually added to his equations in 1917 and then famously called his greatest blunder when Edwin Hubble's observations showed the universe was expanding. It turns out that term may have been right all along, just for different reasons than Einstein imagined. But the cosmological constant is less an explanation and more a description. It says that empty space has an inherent energy to it, vacuum energy, that drives expansion. Why that energy has the specific value it does, why it isn't zero or vastly larger, why it has exactly the value needed to drive the expansion we observe, nobody knows. The value predicted by quantum field theory and the value measured by astronomers differ by something like 120 orders of magnitude. That discrepancy between what our best theory of the very small predicts and what our best observations of the very large measure has been called the worst prediction in the history of physics. The universe is telling us something with that discrepancy. We don't speak the language yet. Now let's talk about what dark energy means for the future, because this is where the terror of deep space stops being about the present and becomes something stranger and colder, a terror that operates on timescales so vast they lose all human meaning, but that are written into the laws of physics as surely as anything else. If dark energy continues to drive the accelerating expansion of the universe, and current evidence and strongly suggests it will, then the universe has a trajectory, and that trajectory is, from a certain perspective, deeply melancholy. Right now we can observe galaxies billions of light years away. We can see the light that left them when the universe was young, but the universe is expanding. The further away a galaxy is, the faster it is receding from us, not because it's moving through space, but because the space between us and it is stretching. For galaxies beyond a certain distance, called the Hubble horizon or the cosmic event horizon, space is expanding between us and them faster than the speed of light. Not violating relativity, light speed is still the local speed limit, but the space between us is growing faster than light can cross it, which means light from those galaxies will never reach us. They are effectively beyond our observable universe already, and as time goes on, more and more galaxies will cross that horizon. The accelerating expansion will push them beyond detectability. In roughly 150 billion years, every galaxy outside our local group, which will by then have merged into the single entity called Milky, will have receded beyond the cosmic horizon. A civilization that arose in that distant future, on a planet in the merged galaxy, would look out at the universe and see nothing, no other galaxies, no evidence that the universe contains anything beyond their own island of stars, no cosmic web to map, no distant supernovae to measure expansion with, no way to discover the Big Bang from observational evidence, because the cosmic microwave background radiation, the afterglow of the Big Bang that we can detect today, will have redshifted to wavelengths so long they'd be undetectable. That future civilization would have no way of knowing what we know. They would look out at a universe that appeared to consist of a single galaxy surrounded by infinite empty darkness, and they would be wrong, but they would have no way to find out we are living in a privileged moment. The universe right now is observable, it is legible. The evidence of its history and structure is available to us in the light that fills our telescopes. That window is open, and on cosmological timescales, it will not stay open forever. The things we are learning right now, with Hubble and Webb and DESI and LIGO, may be things that can only ever be learned at this particular moment in cosmic history. Not too early, we needed the universe to have expanded enough for the Webb to be visible. Not too late, we needed to still be able to see the distant galaxies before expansion sweeps them away. We are living in the universe's sweet spot, and we are, finally, wise enough to know it. But even within this privileged window, there are things we can observe that are almost beyond comprehension in their violence. Events so energetic they make supernova explosions look like candle flames. Objects so extreme they challenge our best physical theories. And we're going to encounter two of them now, as we continue outward into the deep universe. The first is the quasar. A quasar, the name is a contraction of quasi-stellar radio source, is what happens when a supermassive black hole at the center of a young, distant galaxy is actively feeding, swallowing enormous amounts of gas and dust, heating the material in its accretion disk to temperatures of billions of degrees, and releasing energy in the form of radiation and jets of plasma that can be seen across billions of light years. The most luminous quasars shine with the energy of roughly 1 trillion suns. Not 1 trillion stars like our sun, 1 trillion suns worth of energy, from a region of space not much larger than our solar system. The most distant quasar currently known is called J03, observed at a redshift that places it about 13.1 billion light-years away, meaning we're seeing it as it existed when the universe was only about 670 million years old. It contains a black hole of about 1.6 billion solar masses, 1.6 billion times the mass of our Sun, in a universe that was less than 5% of its current age. How a black hole grew that massive, that quickly, is a question that current models of black hole formations struggle to fully answer. It shouldn't have had time to get that big, and yet there it is. The universe keeps exceeding our models, it keeps being more than we expected, and every time it does, we learn something about the limits of our understanding, which is ultimately how science works. The anomalies are the gifts. The things that don't fit are the doors. We need to talk about the beginning, not because we've reached it on our outward journey. In terms of physical distance, we're going to keep pushing further, but because the further out you look in space, the further back in time you're seeing. And at some point, those two things, distance and time, become the same conversation. The edge of what we can observe is not just the edge of space. It is the edge of time itself, the boundary of what has had long enough to reach us since the universe began. So to understand what's out there at the very limits of the observable universe, you have to understand how it all started. And how it started is, in every meaningful sense of the word, bizarre. Cast your mind back. Not 100 years, not a million, not even a billion, all the way back. 13.8 billion years. There was no space, there was no time, there was no darkness. Because darkness requires space to exist in. There wasn't even nothing, in the sense you might imagine nothing, an empty room, a void, a blank expanse waiting to be filled. The concept of emptiness requires somewhere to be empty. And there was no somewhere. And then, in a moment that physics can describe right up to but not quite including, everything began. The Big Bang is one of the most misunderstood events in popular science. It was not an explosion in space. It was an explosion of space. The universe did not expand outward into some pre-existing emptiness. Space itself came into being and expanded, carrying matter and energy with it. Every point in the universe was, in the beginning at every other point. The distance between any two locations was zero. And then it wasn't, and it got less zero very, very fast. In the first fraction of a second, in the first 10 to the negative 43 seconds, a unit of time called Planck time, so small it has no physical meaning in our everyday experience. The universe was in a state so hot and so dense that none of the four fundamental forces we know today existed as separate things. Gravity, electromagnetism, the strong nuclear force, the weak nuclear force, they were unified into a single force in conditions we have no way to reproduce and no complete theory to describe. Our physics breaks down at that boundary. The equations produce infinities and nonsense. The very first instant of existence is, in a precise and technical sense, beyond the reach of our current best understanding. We can describe what happened from about 1/10,000,000th of a trillionth of a trillionth of a trillionth of a second onward. What happened before that, or what, if anything, the word before even means in this context, remains one of the deepest open questions in all of science. What we do know is that extremely shortly after the beginning, within the first tiny fraction of a second, the universe went through a period of extraordinarily rapid expansion called cosmic inflation. In an almost incomprehensibly brief interval, the universe expanded by a factor of at least 10 to the power of 26. Some models suggest far more. The entire observable universe, which today spans about 93 billion light-years, was inflated from a region smaller than a proton to something roughly the size of a grapefruit. That sentence is worth reading again slowly. Everything you can see, every galaxy, every star, every particle of matter in the entire observable universe, all of it was compressed, before inflation, into a space smaller than the nucleus of an atom. Inflation was proposed in 1980 by physicist Alan Guth to solve several problems with the standard Big Bang model. Why is the universe so uniform in temperature across regions that, without inflation, could never have been in contact with each other and therefore had no way to reach thermal equilibrium? Why is the geometry of the universe so precisely flat, so exquisitely balanced between the density that would cause it to collapse and the density that would cause it to fly apart, that our best measurements find it flat to within 1%? Inflation solves both of these problems elegantly. It also makes a specific prediction that the early universe's quantum fluctuations, stretched to cosmic scales by inflation, would leave a particular pattern of temperature variations in the cosmic microwave background radiation. And when we looked, that pattern was there, but inflation raises its own questions. What drove it? What field of energy caused that extraordinary expansion? When and why did it stop? We have candidate theories, the inflaton field, various models of scalar fields with particular properties, but no definitive answer. Inflation is almost certainly something like what happened. The details of why and how remain actively debated. The cosmic microwave background, the CMB, this is the most important image in the history of science, and most people have never heard of it in that context. About 380,000 years after the Big Bang, which sounds like a long time, but is cosmologically speaking an eye blink after the beginning. The universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms for the first time. Before this moment, the universe was a dense, opaque plasma. Light couldn't travel freely because it kept bouncing off free electrons. The universe was literally a fog. You couldn't see through it. When neutral atoms formed, that fog cleared. Photons, particles of light, were suddenly free to travel, and they've been traveling ever since. For 13.8 billion years, those photons have been streaming outward in every direction, gradually losing energy as the universe expanded, shifting from visible light down through infrared, through microwave, all the way to the microwave frequencies we detect today. The cosmic microwave background is the light from that moment. It is the oldest light in the universe. It comes from every direction in the sky with almost perfect uniformity, a temperature of 2.725 degrees above absolute zero, the coldest temperature possible. And when we map the tiny temperature variations in the CMB, fluctuations of about 1 part in 100,000, we see the pattern that inflation predicted, the seeds of every structure that would ever form, the original blueprint of the cosmic web. The quantum fluctuations of the earliest universe, written in the temperature of light that has been traveling for nearly 14 billion years. The Planck satellite, a European Space Agency mission that operated from 2009 to 2013, produced the most detailed map of the CMB ever made. What it found confirmed the standard model of cosmology, the lambda CDM model, with extraordinary precision. The universe is 13.8 billion years old. It is spatially flat. It is made of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These numbers come from a map of ancient light, but the Planck data also revealed a handful of anomalies, features in the CMB that are statistically unexpected under the standard model. A hemispherical asymmetry. One half of the sky is very slightly different from the other. A cold spot, a region significantly cooler than the surrounding CMB, which some researchers have suggested could be the imprint of another universe pressing against ours through the quantum foam of the early cosmos. Most cosmologists treat these anomalies cautiously. They may be statistical flukes, artifacts of how we process the data, or effects we don't yet understand, but they haven't gone away, and some of them are intriguing enough that they continue to generate serious scientific attention. The universe, even in its oldest light, has things it hasn't finished telling us. Now, the observable universe, everything we have talked about, the Moon, Mars, Jupiter, the outer solar system, the interstellar medium, the Milky Way, the local group, the Virgo supercluster, Laniakea, the cosmic web, the quasars, the CMB, all of it fits within the observable universe. A sphere roughly 93 billion light-years in diameter, centered on us, containing everything whose light has had time to reach us in the 13.8 billion years since the Big Bang. And here is the thing that should genuinely stop you in your tracks. The observable universe is not the universe. The observable universe is just the part of the universe we can see, the part whose light has reached us. Beyond the cosmic horizon, beyond that sphere of 93 billion light-years, the universe continues, and based on everything we know about how it formed and how it behaves, it continues for an extraordinarily long way. How far? We don't know. We cannot know by definition. Light from beyond the horizon hasn't reached us and won't. We cannot observe it. We cannot measure it. We can only extrapolate from what we can see, the most conservative estimates, based on the spatial flatness of the observable universe and what that implies about the total extent of space, suggest the total universe is at least 250 times larger than the observable universe in each dimension, meaning its volume is at least a few million times larger. Other estimates, depending on the details of inflationary models, suggest the total universe could be vastly, incomprehensibly larger than that. Some models of eternal inflation, the idea that inflation, once started, never fully stops and keeps spawning new regions of expanding space-time, suggest the total universe is effectively infinite, not large, infinite, unbounded, without edge or limit, an infinite universe, an infinite number of galaxies, stars, planets, an infinite number of places where the conditions for life as we know it might exist, an infinite number of chances for the dice of chemistry and biology to roll in favor of complexity. In an infinite universe, not only is there almost certainly life elsewhere, there would be, if the laws of physics are the same everywhere, an infinite number of places where life exists, an infinite number of planets with something like trees, an infinite number of planets with something like oceans, possibly, and this is where it gets genuinely strange, an infinite number of planets with something like you. In an infinite universe with consistent physical laws and random initial conditions, every configuration of matter that is physically possible will eventually occur, not might, will, and will occur an infinite number of times, including the exact configuration of atoms that makes up your brain, your memories, your sense of self. Somewhere, if the universe is truly infinite, there is another version of this moment happening right now. Not metaphorically, literally. Another you, in another galaxy, watching or listening to something very much like this. This idea, the Level 1 multiverse, as physicist Max Tegmark calls it, requires no exotic physics, no parallel dimensions, no quantum branching, just an infinite universe and the statistics of random initial conditions, and while it cannot be tested or confirmed, it cannot be ruled out either. It follows logically from things we already know. If we take the flatness and apparent uniformity of the observable universe to its logical conclusion, the universe may be infinite, and if it is, you are not unique, but we're not done with the strangeness. Because there's another layer beyond even the infinite expanse of physical space, a question that sits beneath everything we've discussed and that gets asked with increasing seriousness by serious physicists. Why is there something rather than nothing? It sounds like a philosophical question, a late-night conversation kind of question, but it is also, genuinely, a scientific one, because nothing, true nothing, not a quantum vacuum but actual, absolute non-existence, would require active explanation for why it didn't last. Quantum mechanics tells us that empty space is not actually empty. The vacuum seethes with virtual particles, popping in and out of existence, borrowing energy from the universe for the briefest possible moment before annihilating each other and repaying it. The vacuum has energy, the vacuum fluctuates, and some physicists, Lawrence Krauss being perhaps the most prominent popular voice on this, have argued that a universe can arise from a quantum vacuum through processes we partially understand, that something can come from nothing in a quantum mechanical sense. Others push back. They argue that a quantum vacuum is already something. It has laws, it has properties, it exists within a framework of physics. True nothing, they say, has no laws and no properties and cannot fluctuate into anything because fluctuation requires rules and true nothing has none. Where did the rules come from? Where did the framework of physics come from? Why are the constants of nature the values they are? These questions, the fine-tuning problem, the origin of the laws of physics, the reason the universe exists at all, sit at the frontier where physics and philosophy meet and occasionally argue loudly at each other. There are no settled answers, there are frameworks. The multiverse, in its various forms, offers one. If there are an enormous or infinite number of universes, each with different values of physical constants, then we inevitably find ourselves in one where the constants permit complexity and life, because those are the only ones in which someone can ask the question. But this merely pushes the question back a level. Where did the multiverse come from? What are its rules? Why does anything exist at all? We don't know, and that's not a failure of science. That is the frontier of science, the living, burning edge of human understanding, where the questions are so deep and so fundamental that our tools are still being built to address them. Every generation of physicists inherits a universe slightly better understood than the one the previous generation received. The questions change shape, the answers generate new questions, the frontier moves. That is the adventure. That is what it means to be a species that looks up. You are made of atoms forged in stars. You are warmed by a fusion reactor 93 million miles, 150 million kilometers away. You live on a rock orbiting an ordinary star in the outer reaches of a spiral galaxy that is one of roughly 2 trillion galaxies in the observable universe. Your galaxy is being pulled toward a gravitational attractor you can't see, in a universe that is mostly made of things you can't identify, expanding at an accelerating rate, driven by an energy you don't understand, which began in an event your best physics cannot fully describe, in a cosmos that may be infinite in extent, and has certainly been in existence for longer than the human mind can genuinely grasp. And you are here, asking questions, building telescopes, sending spacecraft to the edge of everything, writing equations that predict the behavior of objects a billion light-years away and having those predictions confirmed, listening for whispers from colliding black holes, looking for life in the oceans of distant moons. That is not insignificance. That is, in every measurable sense, the most extraordinary thing we know of in the universe. Let's talk about time, not in the way we usually talk about it. Not clocks and calendars and the feeling that Friday afternoons last forever while weekends disappear in minutes. I mean time as a physical thing, a dimension, a feature of the universe that behaves in ways that should, if you think about them carefully enough, make the hair on the back of your neck stand up. Because here's something that took humanity an embarrassingly long time to figure out, and that most people still haven't fully absorbed, even though it's been confirmed experimentally over and over again for more than a century. Time is not the same everywhere. Einstein figured this out in 1905 with special relativity, and then deepened it in 1915 with general relativity. And what he found, what the mathematics demanded, and what experiments have since confirmed beyond any serious doubt, is that time and space are not separate things. They are woven together into a single four-dimensional fabric called space-time. And that fabric is not rigid, it bends, it stretches, it curves in the presence of mass and energy. And the rate at which time flows depends on where you are in that curved fabric and how fast you're moving through it. This is not philosophy, this is engineering. The GPS satellites orbiting Earth right now have to correct for relativistic time effects every single day. The satellites are moving fast relative to the ground. Special relativity says their clocks run slightly slower because of that speed, but they're also higher up, further from Earth's gravitational field. General relativity says their clocks run slightly faster because gravity curves time, and weaker gravity means time flows more quickly. The net effect is that without corrections, GPS clocks would drift by about 38 microseconds per day relative to clocks on the ground. 38 microseconds doesn't sound like much, but GPS works by timing signals to nanosecond precision. A 38 microsecond daily drift would cause navigation errors of roughly 11 kilometers per day. Your GPS would be useless within weeks if we didn't account for Einstein's equations. Relativity is not abstract theory. It is a practical reality that your phone depends on every time you ask it for directions. But the truly staggering implications of relativistic time don't show up in GPS corrections. They show up when you start thinking about what happens near extreme masses, near black holes, near the kinds of objects we've been talking about throughout this journey. Time dilation near a black hole is not subtle. As you approach the event horizon, that boundary of no return we talked about earlier, time, from your perspective, continues to flow normally. You don't feel it slowing. Your heartbeat, your thoughts, your experience of the seconds passing, all of it seems perfectly ordinary to you. But to someone watching you from far away, your time is slowing down. The closer you get to the event horizon, the more dramatically your clock appears to slow relative to theirs. At the event horizon itself, from the perspective of a distant observer, time appears to stop entirely. You appear to freeze, your image redshifting into oblivion as the light from you struggles against an ever stronger gravitational pull, persists at the horizon for what is, from the outside, effectively forever, but you don't freeze. From your perspective, you cross the horizon, you keep going, you fall inward, and what happens then is where our physics becomes honest about its own limitations. Inside the event horizon, the roles of space and time swap. Outside a black hole, time flows forward and space extends in all directions. You can move through space however you like, but you cannot go backward in time. Inside the event horizon, the singularity at the center isn't just somewhere in space, it is somewhere in time. It is in your future. All future-pointing paths inside a black hole lead to the singularity, the same way all future-pointing paths outside lead forward in time. You cannot avoid the singularity any more than you can avoid tomorrow. The singularity is not a place. It is a when, and at the singularity, the equations of general relativity break down completely. They produce infinite density, infinite curvature, infinitely small volume. Infinities in physics are not answers, they are signs that the theory has been pushed beyond its domain of validity. General relativity, our best theory of gravity and space-time, stops working at the singularity. It cannot tell us what happens there. To answer that question, we would need a theory that unifies general relativity with quantum mechanics, a theory of quantum gravity. And despite decades of effort by some of the most brilliant minds our civilization has produced, we don't have one yet. String theory is a candidate. Loop quantum gravity is another. Neither has yet made a confirmed, unique, testable prediction that distinguishes it from competing theories. Both have their advocates and their critics. Both are mathematically sophisticated and conceptually radical. Neither is settled science. The singularity inside a black hole, the point where everything we know about physics gives way, may be the most important unsolved problem in all of theoretical physics. because whatever replaces the singularity in a correct theory of quantum gravity will tell us something profound about the fundamental nature of space, time, matter, and reality itself. It will tell us what the universe is made of at the deepest possible level. We don't know what that is yet. But there's something even stranger about black holes that has been quietly disturbing physicists for decades and only recently started to see serious progress toward resolution. Something called the black hole information paradox. Here's the problem. Quantum mechanics has a rule, a deep foundational rule that is not a convenient approximation or a simplifying assumption, but a bedrock principle of how the universe works at the quantum level. That rule is that information is conserved, not matter, not energy exactly. Information, the complete description of a physical system, the quantum state of every particle, every interaction, every property of everything in a system cannot be destroyed. It can be scrambled, it can be transformed. It can be hidden so thoroughly that recovering it would be practically impossible. But it cannot, according to quantum mechanics, be truly eliminated from the universe. And then Stephen Hawking came along in 1974 and showed, using a calculation that combined quantum mechanics with general relativity, that black holes are not perfectly black. They radiate very, very slowly through a quantum process at the event horizon. Black holes emit what we now call Hawking radiation, a faint thermal glow that carries energy away from the black hole. Over an extraordinarily long time, for a stellar mass black hole, we're talking timescales vastly longer than the current age of the universe. This radiation causes the black hole to slowly lose mass and eventually evaporate completely. And here is the problem. The Hawking radiation appears to be purely thermal, random, carrying no information about what fell into the black hole. A book, a star, a human being, a cloud of hydrogen, whatever falls in, seems to come out as the same featureless thermal radiation. The information about what went in appears to be destroyed. But quantum mechanics says information cannot be destroyed. So either quantum mechanics is wrong, or general relativity is wrong, or the way we're combining them is wrong, or something entirely unexpected happens at the event horizon, or in the process of evaporation that somehow preserves the information in a form we don't yet understand. This conflict, the black hole information paradox, has been called one of the most important problems in theoretical physics. It's not just about black holes. It's about the compatibility of our two greatest physical theories, general relativity, which governs the large, quantum mechanics, which governs the small. They are both extraordinarily well tested and extraordinarily successful in their respective domains, and when you push them together at the extreme conditions of a black hole, they disagree. Fundamentally, in a way that cannot be papered over, in recent years progress has been made. Ideas involving holography, the conjecture growing out of string theory, that the physics inside a volume of space is fully encoded on its boundary surface, like a three-dimensional image encoded on a two-dimensional hologram, have suggested ways the information might survive. The concept of black hole complementarity, proposed by Leonard Susskind, suggests that from outside the black hole, information is preserved in the Hawking radiation, while from inside, the infalling observer experiences nothing unusual, and that these two pictures are not contradictory because no single observer can ever verify both simultaneously. More recently, calculations involving what are called quantum extremal surfaces have suggested that information does eventually emerge in the Hawking radiation in a highly scrambled form, but a complete, rigorous, universally accepted resolution does not yet exist. What falls into a black hole might not be lost forever, but we're still working out how it gets out. Now let's talk about something that comes up whenever people push hard on the nature of reality at its most fundamental level, something that has moved over the past few decades from the fringes of theoretical speculation toward the mainstream of serious scientific discussion, the simulation hypothesis. I want to be clear about what this is and what it isn't. It is not established science. It is a philosophical and theoretical argument, not an empirically tested model, but it is taken seriously enough by serious people, physicists, philosophers, computer scientists, that it deserves honest engagement rather than dismissal. The argument, most famously articulated by philosopher Nick Bostrom in 2003, and since discussed by figures including Elon Musk, Neil deGrasse Tyson, and theoretical physicist James Gates, goes roughly like this. If it is possible to create a computer simulation of minds and experiences indistinguishable from the real thing, and if civilizations tend to survive long enough to develop such technology, and if some civilizations choose to run such simulations, then the number of simulated minds would vastly outnumber the number of real ones. And if you don't know whether you're simulated or real, simple probability suggests you're more likely simulated. Now, here's where it gets interesting from a physics perspective. James Gates, a theoretical physicist working on supersymmetry, reported finding what appeared to be error-correcting codes, the same kind of codes used in internet browsers, embedded in the equations of fundamental physics. Whether this is a deep clue about the nature of reality or a mathematical coincidence is genuinely debated, and the fact that the universe appears to be quantized at the smallest scales, that space and time may not be continuous but may have a smallest possible unit, the Planck length of about 1.6 times 10 to the negative 35 meters, has led some to note a curious resemblance to the pixelation of a digital system. None of this proves anything, but the question of why the universe is mathematical at all, why nature obeys equations, why abstract structures invented by pure mathematicians turn out to describe physical reality with uncanny precision, is one that serious thinkers have wrestled with for centuries. Eugene Wigner called it the unreasonable effectiveness of mathematics. Max Tegmark has proposed the mathematical universe hypothesis, the idea that the universe is not merely described by mathematics, but actually is a mathematical structure, and that physical existence and mathematical existence are the same thing. These ideas are speculative. They may never be testable, but they emerge from serious attempts to answer serious questions. And in a universe that continues to exceed our expectations at every scale, keeping an open and critical mind about the nature of reality is not naive. It is the only scientifically honest position available. Let's come back to something more concrete, more immediate, something you can actually point to in the sky, even if you can't see it with the naked eye: gamma-ray bursts. If you wanted to design the most violent event the universe is capable of producing, something that would make a supernova look gentle, something that would briefly outshine the entire observable universe in pure energy output, you would design something very much like a gamma-ray burst. Gamma-ray bursts, or GRBs, are detected by satellites like the Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory on average roughly once per day. They appear as brief, blindingly intense flashes of gamma radiation from random directions in the sky. They last anywhere from a fraction of a second to several minutes, and in that brief window, a single gamma-ray burst releases more energy than our Sun will emit in its entire 10 billion-year lifetime. Some estimates put the peak luminosity of the most powerful GRBs at roughly 10 to the power of 47 watts. To put that in perspective, the entire Milky Way galaxy, all 200 to 400 billion stars, all burning simultaneously, has a total luminosity of roughly 4 times 10 to the 36 watts. A single gamma-ray burst can be 10 billion times more luminous than our entire galaxy. There are two main types. Short GRBs, lasting less than 2 seconds, are thought to be caused by the merger of two neutron stars, or a neutron star and a black hole. the same kinds of events that produce gravitational waves, long GRBs lasting more than 2 seconds, are associated with the collapse of extremely massive, rapidly rotating stars. A special type of supernova called a hypernova or collapsar, in which the collapsing core forms a black hole and jets of material are launched at nearly the speed of light from the poles, boring through the star and then through space, beaming gamma radiation in tight cones across the universe. If a long gamma-ray burst occurred within a few thousand light-years of Earth and one of its jets happened to be pointed directly at us, the effects would be devastating. The gamma radiation would strip away the ozone layer on the side of Earth facing the burst, exposing the surface to lethal ultraviolet radiation from the Sun. Some models suggest such an event could trigger a mass extinction event comparable to the ones in Earth's geological past. There is even a hypothesis, not widely accepted but seriously proposed, that the Ordovician mass extinction 440 million years ago, which wiped out roughly 85% of marine species, may have been caused or contributed to by a gamma-ray burst in our galactic neighborhood. The nearest known long GRB candidate, a star called WR104, a Wolf-Rayet star about 8,000 light-years away, was once thought to potentially be oriented with its rotational axis pointing toward Earth, which would direct any burst jets our way. More recent analysis has suggested the axis is probably tilted away from us. Probably. The uncertainty remains. The universe fires weapons capable of sterilizing planets at random intervals, from random directions, with no warning, and yet, here you are, billions of years into the universe's history, on a planet that has somehow avoided every extinction-level catastrophe long enough for complex life to develop, for intelligence to emerge, for curiosity to flourish, for telescopes to be built and pointed outward and questions to be asked. The universe has had ample opportunity to end the human story before it began. Supernovae, gamma-ray bursts, asteroid impacts, volcanic winters, glaciations, magnetic pole reversals, nearby stellar flares. The list of things that could have derailed the path from single-celled organisms to a species that builds gravitational wave observatories is almost comically long, and yet here we are. There's a concept in cosmology and astrobiology called the anthropic principle. In its weak form, it simply says that the conditions we observe in the universe must be compatible with the existence of observers, because if they weren't, there would be no one here to observe anything. This sounds almost tautological, almost too obvious to be interesting, but its implications are subtle and deep. It means that our very existence selects for certain properties of the universe, not because the universe was designed for us, but because we could only arise in a universe that permitted us. The fact that we find ourselves in a universe with the right physics for complexity doesn't require a designer. It may simply reflect the fact that we are the kind of creatures who could only ask such questions in the kind of universe that made us possible. Whether that comforts you or unsettles you probably says something about you. Let's push a little further. Because we've been talking about the universe we can see, the universe we can measure, the universe whose light has reached us, but modern cosmology and theoretical physics have increasingly serious reasons to consider the possibility that our universe, the entire observable universe, all 93 billion light-years of it, everything we have ever detected or described or imagined, might be just one of many, the multiverse, not science fiction, not a metaphor, a genuine, seriously debated scientific and philosophical framework that emerges from multiple independent lines of reasoning in modern physics. We already touched on the level 1 multiverse, the possibility that an infinite physical universe contains an infinite number of regions with the same laws of physics but different initial conditions, producing an infinite variety of cosmic histories. But there are other levels, The level 2 multiverse emerges from eternal inflation. If inflation, that period of extraordinarily rapid expansion in the very early universe, never fully stops but instead continues in some regions while ending in others, it would produce a vast landscape of pocket universes, each one a bubble of space that stopped inflating and settled into its own post-inflationary state. Each bubble universe could have different values of physical constants, different amounts of dark energy, different particle masses, a different physics. Ours would be one bubble among an effectively unlimited number, each one separated from the others by expanding inflationary space so fast-moving that the bubbles can never collide or communicate. This kind of multiverse is not a speculation added to inflation for philosophical reasons. It is a natural consequence of many inflationary models. If inflation happened, and the evidence strongly suggests it did, eternal inflation may be unavoidable, and if eternal inflation is real, the level 2 multiverse may be real. The level 3 multiverse comes from quantum mechanics. The many worlds interpretation, originally proposed by Hugh Everett in 1957 and increasingly seriously regarded by physicists today, suggests that quantum mechanical wave function collapse, the process by which a quantum system in a superposition of states appears to resolve into a single outcome when measured, doesn't actually collapse at all. Instead, every possible outcome occurs, and the universe branches into separate, non-interacting copies, each one containing a different outcome. Every quantum event that can go multiple ways does go multiple ways, in different branches of a constantly splitting universal wave function. The universe is not choosing, it is doing everything. These ideas are not comfortable. They are not supposed to be. They represent the universe pushing back against our instinct that we are the center of things, that our history is the history, that our cosmos is the cosmos. The Copernican revolution took us from the center of the solar system to one planet among several. Then we learned our solar system is one of hundreds of billions in the galaxy. Then we learned our galaxy is one of trillions in the observable universe. The multiverse, if any version of it is correct, is the next step in that same long demotion. We are not at the center, we never were. And our universe may not even be the universe. It may be one universe, one of an almost unlimited number. But here is what I want you to hold on to. Even as the scale keeps growing and the ground keeps shifting beneath your understanding, the fact that we figured this out, us, on this small planet, in this ordinary galaxy, in this one pocket of space-time, is not diminished by the possibility that we are one of infinitely many. If anything, it is more remarkable. In the vast, overwhelming, mostly empty, mostly dark, mostly indifferent expanse of everything that exists, there is this. A species that looked up, that asked questions, that built instruments of extraordinary delicacy, that wrote equations describing the behavior of things they would never touch and never visit. And that found in the asking something that feels very much like meaning. You are that species. This is your universe. Let's talk about the end. Not the end of a day or a civilization or even a species. I mean the end of everything. The final chapter of the universe itself, written in the laws of thermodynamics and the mathematics of particle physics and the slow, patient, utterly indifferent arithmetic of deep time. Because here's something that doesn't get talked about enough. The universe has a future, a very, very long future, and the further you travel into that future, the further out in time rather than space, the stranger and emptier and more final it becomes. And just like our journey outward through space revealed layer after layer of strangeness, the journey forward through cosmic time reveals something similar, something that starts familiar and ends in a silence so complete and so absolute that silence itself feels like the wrong word for it. So let's go there. Let's walk the universe forward to its end, step by step, in the only way that a species as brief as ours can, by following the physics, Right now, we live in what cosmologists call the stelliferous era, the age of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited, and it will last for another roughly 100 trillion years, 10 to the power of 14 years. 100 trillion years. Our universe at 13.8 billion years old is barely an infant. We are in the early morning of the stelliferous era, nowhere near its midpoint, with an almost incomprehensible stretch of star-filled time still ahead of us. During the stelliferous era, stars form, burn and die. Massive stars live fast and die violently in supernovae, scattering heavy elements into the interstellar medium to be incorporated into the next generation of stars and planets. Medium-sized stars like our Sun live for billions of years, fusing hydrogen into helium in their cores, and then swell into red giants before shedding their outer layers as planetary nebulae and leaving behind white dwarfs, dense, hot remnants about the size of Earth, slowly cooling over billions of years. Small stars, red dwarfs, burn so slowly and so efficiently that the smallest ones will still be fusing hydrogen trillions of years from now, long after our Sun is dead and cold. Our Sun, for the record, has about 5 billion years left on the main sequence. In roughly 5 billion years, it will exhaust the hydrogen in its core and begin to swell into a red giant. Its outer atmosphere will expand outward, eventually engulfing Mercury and Venus, and possibly Earth, though the details depend on how much mass the Sun loses during the red giant phase, which affects the orbital dynamics. Whether Earth is swallowed or merely scorched, it will not be a place where anything survives. The oceans will boil away in roughly 1 billion years as the Sun gradually brightens, even before the red giant phase. Complex life on Earth's surface, if it still exists by then, faces a deadline on a timescale that makes the age of the dinosaurs look like a brief afternoon. In the very long run, a few tens of billions of years into the red giant phase, the Sun will shed its outer layers, creating a planetary nebula of glowing gas, and what remains will be a white dwarf, a dense, slowly cooling ember roughly the size of Earth, made mostly of carbon and oxygen, with no fusion occurring in its core. It will radiate the heat it accumulated during its hydrogen-burning life, gradually cooling over billions and billions of years, until it eventually reaches the temperature of the surrounding space and becomes what's called a black dwarf, a cold, dark, inert crystal of degenerate matter. The time for a white dwarf to cool to a black dwarf is longer than the current age of the universe by many orders of magnitude. And here's a remarkable detail: because the universe is only 13.8 billion years old, there are currently no black dwarfs anywhere in the observable universe. None. Not a single one. The universe hasn't been around long enough for any white dwarf to have cooled that completely. Every white dwarf in existence right now is still warm, still glowing, however faintly. The first black dwarfs won't appear for an almost incomprehensible span of time yet to come. We exist too early to have witnessed the death of a star, completed all the way to cold silence. Now let's skip forward, way forward, past the end of the stelliferous era. Roughly 100 trillion years from now, the universe enters the degenerate era. Star formation has essentially ceased. The raw material, the hydrogen gas in galaxies, has been used up or dispersed. The great molecular clouds that once collapsed under gravity to ignite new suns are gone. The universe still contains objects, white dwarfs cooling toward black dwarfs, neutron stars, black holes, but the night sky, if there were anyone to see it, would be almost completely dark. The brilliant, crowded, living galaxy we inhabit would be a graveyard of cooling embers and silent, invisible remnants. This era lasts from roughly 10 to the power of 15 years to about 10 to the power of 40 years. Numbers so large they require new language to hold. 10 to the power of 40 years are 1 followed by 40 zeros. In that span, something interesting happens to the stellar remnants. Quantum tunneling, the quantum mechanical process by which particles can pass through energy barriers they classically shouldn't be able to cross, begins to matter in new ways. White dwarfs may eventually crystallize completely. Protons, if they decay, which some extensions of the standard model of particle physics predict, would begin to do so on timescales of around 10 to the power of 34 to 10 to the power of 40 years. Proton decay, the spontaneous disintegration of the protons that make up the nuclei of every atom in your body, in every planet, in every stellar remnant. If it happens, and we haven't yet experimentally confirmed it, despite enormous sophisticated experiments in underground detectors, watching enormous tanks of water for the telltale signatures of a single proton decay, then all ordinary matter eventually dissolves. Not into nothing, but into lighter particles, photons, electrons, positrons, eventually settling toward equilibrium. Every planet, every white dwarf, every neutron star, everything made of atoms, over these almost unfathomable timescales, gradually falls apart. The experiments searching for proton decay, like Super Kamiokande in Japan, a detector containing 50,000 tons of ultra-pure water deep underground, watching for the flash of Cherenkov radiation that a single decaying proton would produce, have so far found nothing. This places lower limits on how long a proton must live. The current experimental lower limit is roughly 10 to the power of 34 years, which is longer than the universe has existed by an enormous factor, but which is still within the range of some theoretical predictions. We are still looking. The answer matters enormously for what the very far future of the universe looks like. If protons decay, matter as we know it is temporary. If they don't, some forms of matter persist far longer into the future, and the story of the universe's end has a different, though not ultimately more optimistic, trajectory. Further still, past the degenerate era, we enter what cosmologists grimly call the black hole era, roughly 10 to the power of 40 to 10 to the power of 100 years from now. By this point, whether or not proton decay has dissolved ordinary matter, what remains are black holes, the stellar mass ones, the supermassive ones at the centers of what were once galaxies. In a universe stripped of stars, stripped of planets, stripped of atoms, if proton decay occurred, black holes persist. They are, in a sense, the last survivors, the final structures in a universe that has run out of almost everything else. And then, slowly, they too begin to die. Hawking radiation, that quantum process we talked about in Part 7, by which black holes very slowly radiate energy and lose mass, eventually wins. Given enough time, every black hole evaporates. The timescale depends on mass. A stellar mass black hole of around 10 solar masses would take roughly 10 to the power of 74 years to evaporate completely through Hawking radiation. A supermassive black hole of 1 billion solar masses, like the ones sitting at the centers of large galaxies, would take roughly 10 to the power of 96 years, 10 to the power of 96 years. That number is so large that if you tried to write it out, a 1 followed by 96 zeros, the number itself would have more digits than there are atoms in the observable universe. And yet it is a finite number, and at its end the last black hole sputters and dies in a final burst of Hawking radiation, a brief fading flash in an otherwise perfectly dark and nearly perfectly empty universe. And after that, the dark era. Beyond roughly 10 to the power of 100 years, the universe reaches what may be its final state, a vast, cold, almost perfectly empty expanse, populated only by the lightest stable particles. Photons of unimaginably long wavelengths, redshifted almost to nothing by billions of years of cosmic expansion, electrons and positrons drifting impossibly far apart, neutrinos, gravitons. The temperature of the universe, already barely above absolute zero today, at 2.7 degrees, has fallen to a number so close to absolute zero that the difference is unmeasurable. The universe is in a state of maximum entropy, Maximum disorder, maximum uniformity, minimum usable energy. This is the heat death, the state toward which the second law of thermodynamics has been pointing since the universe began. Not an explosion, not a collapse, not a dramatic finale, just stillness, just cold, just the quiet settling of everything into the lowest possible energy state, spread across a universe so vast that even the concept of locality has ceased to have meaning. There are no stars, there are no planets, there are no atoms, there are no structures of any kind at any scale. There is just the universe, infinite and dark and cold and silent, having exhausted every source of gradient, every difference in temperature or density or energy that could have driven any process, any event, any change of any kind. Nothing happens, nothing can happen. The universe exists in a state of perfect, eternal stillness. This is where physics, as we currently understand it, says things end. But, and this is the part that theoretical physicists genuinely argue about over coffee and in journals, it may not be entirely the end. Quantum mechanics doesn't allow for perfect stillness. The uncertainty principle, Heisenberg's famous relationship between conjugate variables like position and momentum, means that even in a state of maximum entropy, quantum fluctuations persist, virtual particles flickering in and out of existence. And in a universe of infinite time, even the most improbable events become not just possible but inevitable, given enough time, including, theoretically, a Boltzmann brain. This concept, first raised seriously by physicists including Sean Carroll, is one of the more philosophically disturbing ideas in modern cosmology. In a universe of infinite time and quantum fluctuations, random thermal fluctuations could, in principle, spontaneously assemble any configuration of matter, however improbable, including a brain, a fully formed, conscious, thinking brain, complete with false memories of a life that never happened, flickering into existence from the random quantum noise of the universe's final state, existing for a brief moment before dissolving back into chaos. If the universe exists for infinite time in the dark era, and current physics suggests it does, since the final state appears to be stable rather than collapsing, then Boltzmann brains are not just possible, they are, in the infinite fullness of time, inevitable, and they would appear with a frequency vastly exceeding the frequency of real, evolved, embodied minds like yours, simply because there are infinitely many more ways for a random fluctuation to produce a brief, isolated brain than there are paths that lead to an entire universe with stars and planets and biology. This creates a paradox. If you are vastly more likely to be a Boltzmann brain, a random fluctuation with false memories, than a real evolved being, why do you seem to be experiencing a coherent, consistent, richly detailed universe, rather than a single flickering instant of false consciousness? Most physicists take this as evidence that the far future of our universe cannot involve infinite time in a state of maximum entropy, and that our cosmological models must eventually be refined to exclude this possibility, but nobody is sure how. Nobody knows exactly what change to the models would resolve the paradox while remaining consistent with everything else we observe. The Boltzmann brain problem is not considered a crisis, but it is considered a puzzle, a clue that our understanding of the ultimate fate of the universe may still be incomplete. There are alternatives to the heat death scenario, not mainstream, not proven, but seriously proposed and seriously discussed. One is the Big Rip. If dark energy is not a cosmological constant, if its strength is not fixed, but instead grows over time, then the accelerating expansion of the universe could accelerate faster and faster until the expansion rate becomes infinite in a finite time. In this scenario, the universe doesn't slowly cool into stillness. Instead, the expansion becomes so rapid that it tears apart every gravitationally bound structure. First galaxy clusters, separated from each other, then individual galaxies torn apart as local expansion overcomes gravity, then solar systems, then planets, then individual atoms, their electrons ripped away from their nuclei by the accelerating expansion of space. Then, in the final instant, space itself is torn apart, the fabric of space-time shredding into a singularity. The Big Rip, current observations, including the 2024 DESI results that hinted at a possibly evolving dark energy, don't confirm this, but they don't rule it out either. The nature of dark energy remains one of the most important open questions in cosmology, and the difference between a constant dark energy and a growing one is not merely an academic distinction. It is the difference between a universe that fades slowly into cold silence and a universe that violently tears itself apart in a finite time. Another alternative is the Big Crunch. If the universe's expansion eventually reverses, if gravity ultimately wins, the universe could collapse back on itself, growing hotter and denser as everything falls inward, culminating in a singularity that mirrors the Big Bang in reverse. This scenario is considered unlikely given current observations of the universe's accelerating expansion, but cannot be definitively ruled out if our understanding of dark energy turns out to be wrong in specific ways. And then there is the possibility of a phase transition. The vacuum of space, that seething quantum field we talked about, exists in what appears to be a stable or metastable state. But quantum field theory raises the possibility that this vacuum is not the lowest possible energy state, that there exists a true vacuum with lower energy, and that our universe exists in what's called a false vacuum, a locally stable but not globally stable configuration. If this is the case, and physicists are genuinely uncertain whether it is, then a quantum fluctuation somewhere in the universe could at any moment nucleate a bubble of true vacuum. This bubble would expand at the speed of light in all directions, its walls converting everything they pass through into the new lower energy vacuum state, a state with completely different physical constants in which atoms as we know them could not exist. This event is called vacuum decay, and it would propagate at the speed of light, which means you would have absolutely no warning. The bubble wall would arrive at the speed of light. You would not see it coming. In the fraction of a second before it reached you, the universe would look completely normal. And then it wouldn't. And then there would be nothing, not an explosion, not darkness, a region of space with different physics, where the atoms that made up your planet and your body and your thoughts simply could not exist in their current form. This has been called the most terrifying thing in physics. Not because it is likely. Current calculations suggest the vacuum is stable, or at least has an extremely long lifetime, and the discovery of a Higgs boson mass near 125 gigaelectronvolts at the Large Hadron Collider in 2012 placed our vacuum in a region of the phase diagram that physicists sometimes describe as metastable, on the edge between stable and unstable, with a very, very long lifetime. But not infinite, not certainly infinite. We may be living in a bubble of false vacuum that will eventually decay, and when it does, the bubble wall will travel at light speed, and there is nothing in the universe that could outrun it or warn against it. The universe might end, not with a slow cooling, not with a dramatic collapse, but with a wall of different physics expanding silently at the speed of light, rewriting the rules as it goes. And yet here you are, in this moment, in this tiny, extraordinary, cosmically improbable window of time, after the Big Bang cooled enough for atoms, after those atoms assembled into stars, after those stars forged the elements, after those elements drifted into clouds that collapsed into a solar system, after a planet formed in just the right place, after chemistry became biology, and biology became complexity, and complexity became consciousness. Here you are, thinking about all of this 13.8 billion years of cosmic history, assembled into a mind that can contemplate 13.8 billion years of cosmic history. The universe, through you, is looking at itself, not metaphorically. The atoms in your brain are atoms that have been part of stars, part of supernovae, part of the interstellar medium, part of the early solar system, part of the ocean, part of countless other living things before they became you. You are a temporary arrangement of ancient material, doing something that, as far as we can tell, is extraordinarily rare in the cosmos. You are thinking, you are wondering, you are asking why the heat death is coming on a timescale so vast it might as well be infinity from where we stand, that stars will go out, the black holes will evaporate, the last photons will redshift into nothing, the universe will end. But right now, in this moment that sits so improbably at the beginning of everything that remains, the universe is alive with light and fire and motion. There are stars being born right now in clouds of gas and dust, in the arms of spiral galaxies we have photographed and named. There are planets forming around those stars. There is chemistry happening in the dark in molecular clouds, producing the building blocks of biology. There are, almost certainly, minds elsewhere in the cosmos, not proven, not confirmed, but statistically suggested by the sheer, overwhelming numbers of stars and planets and the chemistry we see operating everywhere we look, also looking up, also wondering, also building their instruments and asking their questions and reaching, just a little, into the dark. We are not alone in asking. We may simply be alone in not yet having found the others who are asking with us. If you are still watching, please subscribe to the channel and give this video a like. Your support means the world to me. Takes 1 second, makes all the difference now. Let's come back. Back from the edge of the heat death, back from the evaporating black holes and the vacuum decay and the Boltzmann brains flickering in the dark. Back through the deep time and the dying stars and the cooling white dwarfs. Back through the cosmic web and the superclusters and the filaments and the voids. Back through the Milky Way and its violent, magnificent center. Back through the interstellar medium and the terrifying distances between stars. Back through the outer solar system and the ice giants and the asteroid belt. Back here, back now. Back to the present moment, because after everything we've explored, all that scale, all that strangeness, all that humbling, vertiginous depth of space and time, there is something happening right now, today, in the living practice of science, that is just as extraordinary as anything we've discussed, maybe more so, because it is real and immediate and unfolding in real time, driven by human hands and human minds and instruments of almost supernatural sensitivity that our civilization has spent decades building and launching and coaxing into operation. Right now, as you watch this, the universe is being read, more carefully, more deeply, more precisely than at any other point in human history. Let's talk about what we're finding, the James Webb Space Telescope. If you follow science at all, you've heard the name. But I want to make sure you understand what it actually represents, because the popular coverage often focuses on the pretty pictures, and they are genuinely, breathtakingly beautiful, without fully conveying the scientific revolution they represent. Webb launched on December 25, 2021, after decades of development, delays, cost overruns, and engineering challenges that at various points seemed almost insurmountable. It traveled to a gravitational balance point called the second Lagrange point, about 1.5 million kilometers from Earth in the direction away from the Sun, and spent 6 months carefully unfolding its 18 gold-plated beryllium mirror segments and deploying its tennis court-sized sun shield, a 5-layer structure of a material called Captain, thinner than a human hair per layer, designed to keep the telescope cold enough to detect infrared light from the earliest galaxies. The mirror has to be cold. Webb works primarily in infrared, heat radiation, because the light from the most distant, earliest galaxies has been redshifted by the expansion of the universe from its original visible wavelengths all the way down into the infrared. To detect infrared without the telescope's own warmth drowning out the signal, the mirror and instruments have to be cooled to around -233 degrees Celsius, just 40 degrees above absolute zero. In July 2022, Webb released its first science images, and the scientific community did not just admire them, it tore into them, because what Webb was showing immediately was a universe more complex, more structured, more surprising than models had predicted. The first deep field image, a patch of sky smaller than a grain of sand held at arm's length, contained thousands of galaxies. Some of them were among the most distant objects ever observed, and some of those early galaxies were bigger, brighter, and more mature than they had any right to be at their age. In a universe only a few 100 million years old, you should not find fully formed, massive galaxies. The standard model of galaxy formation, the careful, hierarchical process by which small structures merge over billions of years to build larger ones, predicted a young universe full of small, irregular protogalaxies, not the grand structured systems Webb was finding. This is not a crisis for cosmology. This is what science looks like when it's working. The models are being refined. New physics is being explored. The data is telling us something, and we are listening. Webb has also been doing something that would have seemed almost magical to astronomers of even a generation ago. It has been analyzing the atmospheres of planets orbiting other stars, worlds dozens or hundreds of light years away, planets we will never visit, that we cannot even resolve as anything more than a faint signal in the light of their parent star. By watching those planets pass in front of their stars and measuring how different wavelengths of starlight are filtered by the planet's atmosphere, Webb can tell us what molecules are present. Carbon dioxide, water vapor, methane, sulfur dioxide, the chemical fingerprints of worlds we have never touched. In 2023, Webb detected carbon dioxide in the atmosphere of a planet called WASP-39b, a gas giant about 700 light-years away. Not exciting for life in that case, but proof of concept, proof that the technique works, proof that we can read the air of other worlds from here. And in 2023 and into 2024, the scientific community began very carefully, very cautiously discussing a detection that, if confirmed, would be the most important discovery in the history of science: dimethyl sulfide, a molecule that, on Earth, is produced almost exclusively by biological processes, specifically by marine phytoplankton, appeared to be present in the atmosphere of a planet called K218b, a planet roughly 2.5 times the size of Earth, orbiting in the habitable zone of a red dwarf star called K218, about 120 light-years away. The signal was weak. The uncertainties were significant. The Webb team was careful, deliberately, professionally cautious about what conclusions could and could not be drawn. Other explanations for the detection were not ruled out. Abiotic chemistry can produce dimethyl sulfide in some circumstances. The signal needed confirmation and further analysis. Follow-up observations were planned, but the conversation happened, seriously, in peer-reviewed journals, by careful, credentialed scientists using the most sophisticated space telescope ever built. The possibility of biological chemistry on another world was discussed not as speculation but as a hypothesis to be tested. That is where we are right now. That is the frontier we are standing on. Let's talk about some of the other extraordinary instruments and missions that are actively reshaping our understanding of the cosmos in this very moment. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is on a mission to map the large-scale structure of the universe with unprecedented precision. Over its 6-year primary mission, It will survey roughly 15,000 square degrees of sky, about a third of the entire sky, measuring the positions and shapes of billions of galaxies out to distances of 10 billion light-years. Its goal is to understand dark energy and dark matter by studying how the cosmic web has evolved over time and how gravitational lensing distorts the shapes of distant galaxies. Euclid's first science images, released in 2024, demonstrated the extraordinary sharpness and sensitivity of its instruments. This mission will produce the most detailed map of the universe's dark components ever assembled, and its data will be analyzed by scientists for decades. The Dark Energy Spectroscopic Instrument, DESD, mounted on the 4-meter Mayol telescope at Kitt Peak National Observatory in Arizona, has been building a three-dimensional map of the universe by measuring the spectra, and thus the distances of tens of millions of galaxies and quasars. In 2024, DESI released results from its first year of full operations, covering over 6 million galaxies and quasars. The results were striking. The data hinted that dark energy might not be a simple cosmological constant, that its strength might have varied over cosmic time. If confirmed by future data, this would be a genuinely revolutionary finding, overturning the simplest version of our cosmological model and opening a door to new physics. The key word is hinted. The signal was at the level of roughly 2 to 3 sigma, suggestive but not yet definitive by the standards physicists require for a confirmed discovery, which is 5 sigma. More data is coming. More analysis is underway. But the cosmos, once again, appears to be more complex than the simplest model suggested. Gravitational wave astronomy, the field that was essentially born in September 2015 with that first LIGO detection, has matured into a full scientific discipline in an extraordinarily short time. The LIGO-Virgo-Cagra network has now detected over 90 confirmed gravitational wave events, spanning black hole mergers, neutron star mergers, and possibly mixed mergers of black holes with neutron stars. Each event is a window into some of the most extreme physics in the universe, a cosmic laboratory operating at conditions no human instrument could ever reproduce. The neutron star merger detected in August 2017, known by its technical designation GW17817, was particularly remarkable. It was detected simultaneously in gravitational waves and in electromagnetic radiation across the entire spectrum, from gamma rays to radio waves. A gamma ray burst was detected just 1.7 seconds after the gravitational wave signal. Optical telescopes around the world were alerted and began observing within hours, watching the glow of what's called a kilonova, the radioactive afterglow of material ejected by the merger, and in that kilonova glow, astronomers directly observed the production of heavy elements, gold, platinum, uranium, the rapid neutron capture process, the R process, that theorists had long believed was responsible for forging the heaviest elements in the universe, observed in action in real time confirmed. The gold in your jewelry, the platinum in your electronics, the uranium in nuclear reactors. It was forged in events like this one, 2 neutron stars, each the mass of the Sun compressed into a sphere 20 kilometers across, spiraling together over billions of years and finally colliding in a fraction of a second, releasing more energy than the Sun will produce in 10 billion years and scattering the debris of their collision, including every heavy element heavier than iron, into the surrounding space, to be incorporated eventually into new solar systems, new planets, new life. The gold in any ring on any finger anywhere on Earth was made in a collision like that one, in an event so violent it rippled the fabric of space-time and sent a gravitational wave across the universe that we detected a billion years later. Wear that knowledge like jewelry. Let's talk about what's coming next. Because the present is extraordinary and the near future of observational astronomy and space exploration is, If anything, even more exciting, the Nancy Grace Roman Space Telescope, named for NASA's first chief of astronomy, one of the key figures behind the Hubble Space Telescope, is scheduled to launch in the late 2020s. It will have the same resolution as Hubble, but a field of view roughly 100 times larger, allowing it to survey vast swaths of sky with Hubble-quality sharpness. One of its primary science goals is to detect thousands of exoplanets through microlensing, a technique that uses the gravitational bending of light by foreground stars to reveal planets that would be otherwise undetectable. Roman will extend our census of planetary systems throughout the galaxy, helping us understand just how common or rare Earth-like worlds might be. The Vera C. Rubin Observatory in Chile, named for the astronomer whose observations of galaxy rotation curves provided some of the strongest early evidence for dark matter, is preparing to begin its legacy survey of space and time. Over 10 years, it will photograph the entire visible southern sky every few nights, building a dynamic, time-evolving map of billions of astronomical objects. It will discover an estimated 17 million variable stars, hundreds of thousands of supernovae, millions of solar system objects, and potentially revolutionize our understanding of transient events, things that change or explode or disappear on human timescales. NASA's Europa Clipper, which launched in October 2024, is on its way to Jupiter and will begin its orbital survey of Europa in 2030. It will make roughly 50 close flybys of the Moon, using radar to probe the ice shell, spectrometers to analyze the surface and plumes, magnetometers to characterize the subsurface ocean. Its goal is not to detect life. Its instruments are not designed for that. Its goal is to determine whether Europa is habitable, whether the ocean is the kind of place where life could survive. And if that answer comes back yes, as many scientists expect it will set the stage for a future mission that goes further, one designed to actually look. The LISA mission, the Laser Interferometer Space Antenna, is a gravitational wave observatory being developed by the European Space Agency, currently targeted for launch in the mid-2030s. Unlike ground-based detectors like LIGO, LISA will consist of 3 spacecraft flying in a triangular formation with arms 5 million kilometers long, using laser interferometry to detect gravitational waves at much lower frequencies than LIGO can access. This will open an entirely new window on the universe, allowing detection of mergers between supermassive black holes, the gravitational wave background from the early universe, and possibly unexpected sources we haven't imagined yet. LISA will hear the universe at frequencies LIGO is deaf to. It will be like switching from hearing only bass notes to suddenly perceiving the full range of sound. And then there is the Square Kilometre Array, the SKA, a radio telescope network currently under construction in South Africa and Australia, with thousands of antenna dishes and dipoles spread across thousands of kilometers, working together as a single instrument of extraordinary sensitivity. The SKA will be the largest scientific instrument ever built. It will study everything from pulsars to the cosmic dawn, the epoch when the first stars ionized the intergalactic medium and the universe lit up for the first time. It will search for radio signals from other technological civilizations. It will probe the magnetic fields of galaxies. It will watch hydrogen in galaxies across the universe, tracing the evolution of cosmic structure with a clarity we have never achieved. We are building our eyes bigger and more sensitive, and the universe is responding by showing us more and more of itself. And speaking of other civilizations, let's address it directly, because we've been circling it throughout this entire journey, and it deserves to be looked at straight: the search for extraterrestrial intelligence. SETI. In 1960, astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars and listened. He heard nothing of artificial origin, but the act, The idea that we could search systematically, scientifically for signs of other minds in the cosmos sparked a field of inquiry that has never stopped. The Drake equation, which Drake formulated in 1961 to structure thinking about the abundance of technological civilizations in the galaxy, is not a calculation with a known answer. It is a framework for organizing our ignorance, a way of mapping the questions we need to answer to understand whether we are alone. The numbers have changed enormously since 1961. The rate of star formation, known, the fraction of stars with planets, dramatically higher than anyone suspected, thanks to Kepler and TESS and ground-based surveys that have now confirmed over 5,500 exoplanets, with estimates suggesting virtually every star in the galaxy hosts at least one planet. The fraction of those planets in habitable zones, better constrained than before, though still uncertain. The fraction of habitable planets where life actually emerges, unknown. The fraction where intelligence develops, unknown. The fraction of intelligent civilizations that develop detectable technology, unknown. The average lifespan of a technological civilization, the most frightening unknown of all, and one that concerns us as much as it does anyone we might hope to contact. The Fermi paradox, Enrico Fermi's famous lunchtime question, if the universe is full of civilizations, where is everybody, remains unanswered. The silence of the cosmos, despite decades of increasingly sensitive searches, is a fact that admits many possible explanations. Perhaps life is rare, perhaps intelligence is rare, perhaps technological civilizations are self-limiting in their lifespan, perhaps they exist but communicate in ways we haven't thought to look for, or at frequencies we haven't tuned to, or they've moved beyond radio communication entirely in the time since their signals were sent. Perhaps the distances are simply too vast and we're looking in the wrong direction at the wrong time. Or perhaps, and this is the explanation that requires the most careful, critical thought, we are genuinely among the first. Perhaps the universe is young in the relevant sense. Perhaps the conditions for life like ours have only recently become widespread enough, the heavy elements seeded broadly enough through enough generations of stellar evolution for technological civilizations to begin emerging, and we are in the early cohort. Perhaps the galaxy will be full of minds in 1 billion years. Perhaps we are the ancestors. No explanation for the Fermi paradox is proven. None is ruled out. What we can say is this: the search continues, with better instruments, with broader frequency ranges, with new techniques, including looking for laser signals rather than radio, and looking for megastructures, large-scale engineering projects that would betray a technological civilization by the way they alter the light of their star. The Breakthrough Listen initiative, privately funded and scientifically rigorous, has been conducting the most comprehensive SETI search in history, covering more stars, more frequencies, and more target types than any previous effort. We are listening harder than we ever have, and we haven't heard anything yet. But the silence is data too. Every null result narrows the space of possibilities. Every frequency range we rule out points us more precisely at where to look next. The search for another mind in the universe is not naive. It is one of the most important scientific endeavors our civilization has ever undertaken, because the answer, in either direction, changes everything. If we find something, the universe is full of life and we are not alone, and every assumption we have ever made about our uniqueness is overturned in an instant. If we never find anything, if the silence persists indefinitely, then the responsibility we carry for the flame of consciousness, the fact of awareness, the existence of minds that can contemplate the cosmos, that responsibility becomes staggering, because if we are alone, then we are the universe's only way of knowing itself. And what happens to us matters not just to us, but to everything. There is a particular kind of awe that comes from all of this, Not the comfortable awe of a pretty sunset or a starry night, though those are real and beautiful. A deeper awe, the kind that has a slight edge of vertigo to it, the kind you feel when you genuinely try to hold the scale of things in your mind all at once and find that your mind can't quite close around it. When you really sit with the fact that you are a temporary arrangement of atoms on a small rock around an ordinary star in a galaxy that is one of 2 trillion, in an observable universe that may be a tiny fraction of the whole, in a cosmos that has been running for nearly 14 billion years and will continue for a span of time so vast that 14 billion years is, by comparison, the first fraction of a second. That vertigo is not a problem to be solved. That vertigo is the feeling of understanding something true about reality. It is what genuine comprehension feels like when the thing you're comprehending is the universe. And here is what I want you to take from it: the terror of space, the distances, the radiation, the silence, the violence, the indifference, the scale is real. Everything we've described is real. The universe is not warm and welcoming. It did not design itself around us. It did not soften its edges for our comfort. It is vast and cold and violent and mostly empty and running on physics that doesn't care whether you understand it or not. You understand it. A little. More than any previous generation did. More than the species that came before us. More than anyone who ever looked up at the night sky and wondered before they had the tools to find out. You are part of the first generation of humans who knows that planets orbit other stars, the first who has seen a black hole, the first who has heard gravitational waves, the first who has tasted the atmosphere of another world and found carbon dioxide and water and organic molecules, the first who has sent spacecraft to the edge of the solar system and received transmissions back, faint and precious, from interstellar space. You live at the most extraordinary moment in the history of human curiosity, and the journey is nowhere near finished. We started with a question, a simple one on the surface. Why does space get more terrifying the further you travel? It sounds like the setup for a list, a countdown, 10 scary facts about the cosmos delivered with dramatic music and a deep voice. But that's not what this has been, and if you've made it here, through all of it, through the Moon and Mars and the Kuiper Belt and the Oort cloud and the interstellar medium and the galactic center and the cosmic web and the CMB and the multiverse and the heat death and the search for other minds, then you already know that. This has been something else, a journey, a real one, not the kind where you arrive at a destination and take a photograph and go home, the kind where the traveling itself changes you, where each leg of the trip reveals something that reframes everything that came before it, where by the time you reach the furthest point, you are not the same person who started. Let me take you back to the beginning of that journey, and then let's look at where we actually ended up. You started at home, on Earth, on a planet so familiar that most of us have stopped seeing it clearly. A blue and white marble, roughly 12,700 kilometers across, wrapped in a thin skin of atmosphere, thin enough that if the Earth were the size of a standard classroom globe, the atmosphere would be thinner than a coat of varnish, thin enough that the boundary between the air you breathe and the vacuum of space is, on the scale of the planet, almost nothing. And yet that thin skin is everything. It holds the pressure that keeps your blood from boiling. It filters the ultraviolet radiation that would otherwise shred your DNA. It redistributes heat from the equator to the poles. It contains every breath every human being has ever taken, every word ever spoken, every song ever sung, every exhaled moment of every life. It has all happened inside that thin, fragile, irreplaceable varnish on a rock in space. From your front yard on a clear night, you can see roughly 2,000 to 5,000 stars with the naked eye. They look close, they feel intimate. Ancient humans built their entire cosmologies around them: navigation, agriculture, mythology, religion, identity. The stars felt like a ceiling, not a beginning, like a boundary, not a gateway. We know now that they are not close. The nearest one is 4.2 light-years away. If you drove to it at highway speed, you would be driving for roughly 50 million years. If you sent a radio signal, it would take 4.2 years to arrive, and that is the nearest one. The ones you can see with your naked eye span distances of thousands of light-years, the ones that look like a faint smudge, that's not a star, that's the Andromeda Galaxy, 2.5 million light-years away, 2 trillion stars, visible as a dim blur the size of several full moons if you look carefully on a dark night. The sky above your head is not a ceiling, it is a door, and it opens onto something that has no far wall. But here's what I want you to sit with now that we're at the end. Every step of this journey, from the moon to Mars to Jupiter to the edge of the solar system to the nearest star to the galactic center to the cosmic web to the CMB to the edges of the observable universe, every single step was a step into more strangeness, more violence, more scale, more indifference, more of everything that makes space, by any reasonable human definition, terrifying. The moon, close enough to visit, slowly drifting away, a reminder that even the most familiar things in space are in motion, in flux, impermanent. Mars, a brutal, irradiated desert with a near-vacuum atmosphere, where the delay between a distress call and a response is measured in minutes on a good day. The asteroid belt, not the dramatic obstacle course of movies, but something arguably more unsettling. A vast, sparse graveyard of planetary ambitions, the remnants of worlds that tried to form and never quite managed it, scattered across zillions of kilometers of emptiness. Jupiter, a planet so massive it contains more than twice the material of all the other planets combined, surrounded by radiation belts lethal to any unshielded human, hosting storms that have persisted for centuries, with moons that may harbor life in oceans we have never seen. Saturn, breathtaking and transient, its rings a feature so temporary on geological timescales that future civilizations might not know they ever existed. Its moon Enceladus spraying organic molecules into space like a signal no one designed but no one can ignore. The Kuiper Belt and Oort cloud, the true boundary of our solar system, a shell of frozen debris extending almost halfway to the nearest star, a reminder of how large our gravitational neighborhood actually is and how little of it we have visited. Interstellar space, not empty exactly, but close enough to empty that the distinction barely matters, laced with cosmic rays that punch through spacecraft and human tissue alike, traversable only in theory on human timescales. A distance so vast that our most successful emissary, Voyager 1, launched in 1977, and now further from Earth than any object we have ever built, will take another 300 years just to clear the Oort cloud, the nearest star, hostile to life, erupting with flares that would strip away any unshielded atmosphere, circled by planets that may be barren despite sitting in the habitable zone, reachable only in the imagination of our current civilization, or in the dreams of the ones that come after us. The Milky Way, 100,000 to 170,000 light-years across, containing 200 to 400 billion stars, centered on a supermassive black hole 4 million times the mass of our Sun, surrounded by exploding stars and shredded gas clouds and jets of energy reaching 30,000 light-years into space above and below the galactic plane, the local group, the Laniakea supercluster, the cosmic web. Filaments 100 million light-years long, threaded with the light of billions of galaxies, separated by voids so empty that a photon can cross them for hundreds of millions of years and never encounter anything at all. The observable universe, 93 billion light-years in diameter, containing 2 trillion galaxies, every one of them a collection of hundreds of billions of stars, most of those stars hosting planets. the whole structure threaded through with dark matter we cannot see and driven apart by dark energy we cannot explain. And beyond the observable universe, we don't know. More of the same, perhaps. Infinitely more. Or other universes with different physics, different constants, different histories. Or something we don't have a concept for yet. The observable universe may be the universe. Or it may be a single bubble in a foam so vast that the observable universe is to the whole what a single atom is to the ocean. Every step outward was a step into more. More scale, more violence, more strangeness. More of the things that expose how fragile and small and improbable we are. And yet I want to offer you something, not a consolation, not a feel-good ending that softens the edges of what we've been through together. Something truer than that. Something that holds the terror and the wonder at the same time, because they are inseparable, and any account of the universe that separates them is not giving you the full picture. Carl Sagan, one of the great communicators of science in the 20th century, a man who spent his life trying to convey the scale and strangeness and beauty of the cosmos to anyone who would listen, once said something that has stayed in the minds of everyone who heard it. He said that we are a way for the cosmos to know itself, not a poetic flourish. A statement of fact, the universe for most of its history was not self-aware. The Big Bang produced hydrogen and helium. Gravity gathered that hydrogen into stars. The stars fused hydrogen into heavier elements and then exploded, scattering those elements into the interstellar medium. New stars formed from that enriched material. Planets coalesced. On at least one of those planets, chemistry became biology. Biology became complexity. Complexity became nervous systems. Nervous systems became minds. And minds began to ask, where did we come from? What is this place? How does it work? How big is it? How old is it? How will it end? The atoms in your body were forged in stellar interiors. The calcium in your bones was made in a dying star. The iron in your blood was produced in a supernova. The oxygen you breathe was manufactured in the nuclear furnaces of suns that lived and died before our solar system existed. You are not just in the universe, you are made of the universe. You are a piece of the universe that has organized itself into a shape complex enough to contemplate the whole. That is not a small thing. That may be the most remarkable thing about the cosmos. Not its size, not its age, not its violence, but the fact that it produced, in at least one location and possibly in countless others, the capacity for self-reflection, the capacity for wonder, the capacity for a species to build a machine cold enough to see the CMB, to build a detector sensitive enough to hear space-time ripple, to launch a telescope to the edge of the solar system and read the atmospheres of planets orbiting other stars, and to sit here now, at the end of a very long journey through the cosmos, and feel something, feel awe, feel humility, feel connection. The terror is real. I am not taking it back. Space is not friendly. It is not built for us. The vacuum will kill you in minutes. The radiation will kill you in days. The distances are so vast that they reduce any human time frame to meaninglessness. The forces operating at the scales we've discussed, black holes, neutron stars, gamma-ray bursts, supernovae, galactic collisions, are so far beyond human experience that describing them in human terms requires a constant struggle against the inadequacy of analogy. And our civilization, for all its extraordinary achievements, is extraordinarily fragile. We exist on one planet around one star with no backup. We have not yet developed the technology to move significant numbers of people off this world permanently. We have not yet established a self-sustaining presence anywhere else in the solar system. We have not yet deflected an asteroid on a collision course. We have not yet fully understood the climate system we are currently disrupting. We are a one-planet species in a cosmos that does not offer second chances to civilizations that make critical mistakes. The terror is a call to action, not despair, action. The same curiosity that drives us to understand the universe at its largest scales, the same impulse that built the James Webb Space Telescope and LIGO and the Event Horizon Telescope and the Voyager spacecraft and the New Horizons mission and the Cassini orbiter, that impulse is also the impulse that can solve the problems we face on this world. The same species that can look back 400 million years in cosmic history and read the chemistry of atmospheres on planets 120 light-years away can also figure out how to generate clean energy, how to distribute resources equitably, how to build resilient systems, how to extend the life of the only biosphere we currently have. We are not helpless in the face of the cosmos. We are the cosmos, a part of it, anyway, that has developed the capacity to respond to it, to understand it, to act within it, to protect for as long as we can this astonishing, improbable, irreplaceable flame of consciousness that the universe somehow managed to produce here on this blue dot after 14 billion years of trying. Let me tell you something about the night sky that you may not have considered before. When you go outside on a clear night and look up, the light reaching your eyes has been traveling for years or decades or centuries or millennia or in some cases millions of years. The photons hitting your retina left their sources before you were born, before your grandparents were born, before humanity existed, before our species had language or fire or tools. Some of them left before our solar system formed. You are not looking at the sky, you are looking into the past, and when those photons hit your eye, when your visual cortex processes them and your conscious mind perceives them as stars, something extraordinary happens. The light that traveled across space for all that time, indifferent, carrying information but unable to use it, moving at the speed of light toward no particular destination, enters a mind and is understood. The universe sent out that light with no expectation of return. And yet here you are receiving it, making meaning from it, placing it in context, in a map of the cosmos, in a history of everything that came before. You are the endpoint that the universe did not plan for and could not have predicted. You are the moment when ancient light becomes knowledge. That is not a small thing. That is the most astonishing thing I know. We've been on a long journey, from your front yard to the moon, to Mars, to Jupiter, to the edge of the solar system, to the nearest star, to the galactic center, to the edge of the observable universe, to the question of what came before the Big Bang and what comes after the last black hole evaporates. We've talked about relativity and quantum mechanics, and dark matter and dark energy and gravitational waves, and the CMB and the multiverse and gamma-ray bursts and vacuum decay, and the heat death and Boltzmann brains, and the search for other minds and the extraordinary, ongoing revolution in observational astronomy that is happening right now. Today, as you watch this, we've looked at a universe that is, by any honest accounting, terrifying, vast, violent, cold, indifferent, governed by forces that make human scales feel vanishingly insignificant. And we've found that the terror and the wonder are not opposites. They are the same thing, seen from different angles. The same scale that makes the universe terrifying is what makes it magnificent. The same distances that make space lonely are what make the light reaching your eyes precious. The same indifference that strips away any illusion of cosmic purpose is what makes the fact of consciousness, the fact of you right now, thinking these thoughts, so extraordinary. Space gets more terrifying the further you travel, and it gets more beautiful, and more humbling, and more strange, and more magnificent, and more worth understanding, and more worth protecting, and more worth loving. The universe is not required to be comprehensible, and yet somehow it is, or at least it is edging toward comprehensible, slowly, incompletely, imperfectly, but genuinely, in the hands and minds of a species that has been asking questions for about 300,000 years and has been getting real answers for only about 400 of them. We are just getting started. Now you know how terrifying the universe is. So ask yourself, how would we actually survive crossing it? If everything we just covered made you wonder how humanity would actually survive a journey to another star, click the video on the screen. Trust me, after what you just learned, it hits completely different.